Thank you all for joining us for the third annual Apalachicola National Estuarine Research Reserve Symposium. We have a lot of guests joining us online, so if some things seem a little odd, we're also talking to an audience, a virtual audience. And on that note, for the virtual audience, if you look in the handouts, there is a symposium participant agenda, and on that you'll find a link to the Padlet. On the Padlet, we have all of the presenters' pictures, their a description of their presentation, and an email if you want to get in touch with them. So just a little housekeeping here. We have restrooms down the end of the hall. We have snacks next door here and coffee, but please remember, if you're over there, if you're talking, you know, somebody else will be talking here. So, and then please join us this evening for our reception at 4. And we'll have several breaks today. We'll have a break at 10:30, then we'll break for lunch at 12:10, and then break again in the afternoon at 2:30. Without further ado, I'd like to introduce our manager, Jenna Harper.
Thank you, Anita. Appreciate that. Welcome everybody to the third, I'll say annual Apalachicola NERR Research Symposium. We'll see if everything goes well today. We'll do it again next year, right? No, we'll see. So first, I'd like to kick off the meeting by sharing a couple things that really I appreciate most about the Research Reserve system and things that I'm most proud about for our reserve. And the first thing is that we have an amazing research and monitoring program. And it's not just our research program, our researchers, it's also our stewardship program. They do amazing work. They're out there right now doing work. And one of the other really cool things that they do is they partner with researchers all over the place. I mean, we work with local and state and federal agencies. We work with different universities. They might be local universities or some across the country. And it's amazing that they are able to build these partnerships and really like accomplish some really important priority research. So so proud of that. The other thing that I'm really just kind of amazed and proud of all the time is our efforts to take our science and bring it to management. And that is through our coastal management program, our coastal training program. What's I say, coastal management? Not managing, right, Anita? Coastal training program and our education program. And that is really where we hope to touch our local stakeholders, our decision makers, our local community members, visitors to the reserve, our young people. And so saying that, I want to first acknowledge and say kudos to all of the staff that really put on the symposium. And that's anything from building these relationships and supporting them. Some of these have been years-long relationships. Some of them are newer. And I also want to acknowledge all the people that really go into producing the symposium and bringing you all here today in the room and also here online. So thank you first to all of the staff. It is my pleasure this morning to introduce Dr. Mark Rains as our keynote speaker. Dr. Rains is a professor at the University of South Florida and the former director of the USF School of Geosciences. His research focuses on ecohydrology and hydrogeology, specifically controls on ecosystem structure and function in fresh, brackish, saline, and hypersaline aquatic ecosystems. So I think that's everything, right? That's pretty much everything. So everywhere, he's everywhere. In 2021, Dr. Rains was appointed to be our state chief science officer by the governor. He leads the Office of Environmental Accountability and Transparency within the Florida Department of Environmental Protection. And personally, when I found out Dr. Rains was going to be our CSO, I was really excited after hearing his background because of all the challenges that we've had over the years with the Apalachicola Bay River and Bay system. And I think he has a unique background and expertise that is going to be, you know, very informative and helpful to us over the years. But I'm also really excited that Dr. Raines is our CSO because he has a great relationship with the research reserve system and with working with students and fellows within the reserve system. And so that is near and dear to my heart and something I very much appreciate. So without further ado, I'd like to introduce Dr. Mark Raines.
Well, thank you, Jenna. I am a huge fan of the NERRS system and a big user. I'll come back to that a little bit later on. So I do appreciate the opportunity to come back and give back in whatever way I can. So you've heard about my basic background. I mean, I probably wrote what you read, yeah. but I might say it a little differently now. I'm interested in how water connects landscapes from ridge to reef and controls the structure and function of those ecosystems along the way. It makes me sort of perfectly suited, I think, for the role of the CSO, whether I'm good at it or not. But the fact is that most of our challenges are water quantity and water quality. And we're sort of in an unprecedented time in that sense. And I know that a lot of times we spend, I think, sort of a disproportionate amount of time talking about climate change. And I think we should, in the sense that it's sort of presents an existential threat, especially in places like this. But sometimes I think it saps the oxygen from another challenge, which is land use, land cover change. That's like climate change. The manifestation of that is still sort of off into the future. We're starting to see the glimmers of it. But the land use, land cover change has been going on for a long time. We're well over 150 plus years into an uncontrolled experiment, which is to say, what happens when you transform Florida from largely natural to a largely built environment? And I'll give you an example from some of our own work, and one of my co-PIs and wife, Raines, is here, so I'm stealing some of her work, but for good reason. So we've gone back, this in St. Lucie County. I'm not picking on St. Lucie County. In fact, I think they're sort of an exemplar of a county that's sort of looked forward. But to do so, they've looked backward. We've mapped all the wetlands. We've back to the old public land survey system maps and notes, some old military maps and notes. We mapped all the wetlands and channels in the 1850s. And then we did it again today. So that time, 1850s to 2020, they've lost more than 90% of their wetlands. That's probably expected, right? I mean, that's like the story nationwide. But maybe more importantly, or more astoundingly, we mapped all the channels, and in the 1850s, there was 1/10 of 1 kilometer of channel per square kilometer. Okay? Hardly anything. It's so flat. It's so flat you can see the sunset between the cow's legs. But that was no good for drainage, and it was no good, therefore, for living. So we busied ourselves hacking that up, ditching and draining. And today, there's 25 kilometers of channel per square kilometer in St. Lucie County. Fundamental transformation, right? So if you think about like a drop of water fell out of the sky in the 1850s in St. Lucie County, probably landed in a wetland, probably landed nowhere near a channel. It probably just sat there, didn't go very far before it was either sent back up by ET or taken into deep groundwater storage, or whatever it was carrying, those nutrients it was carrying, probably recycled locally. Right? That's a fundamental property, properly functioning ecosystems. Today, drop of water falls in that same place. It probably doesn't fall in a wetland, probably falls in a built environment, probably ag, this is St. Lucie County, probably falls really close to a ditch, the purpose of which to move the water and whatever it's carrying to the nearest major water body. Why the nearest major water body? Because we don't live or farm there. So that we did that all on purpose. We were trying to protect, infrastructure and human health and safety in urban environments, and bring land into production and increase yields in ag environments. But there was an unintended consequence that we're all living with now. So how do you walk that back, right? So you can't really restore it to the 1850s Florida. I'm sure that was beautiful, but it's sort of incompatible with 22 million residents and 130 million annual visitors and the 4th largest economy by GDP. So we have to science and engineer our way out, right? So we're gonna construct some alternative ecosystem that has some of the properly functioning elements of the old ecosystem, but is compatible with the new socio-ecosystem we live in. And though that's a science and engineering problem, it's fundamentally a people problem. And I think we shouldn't forget that. Like everything in the end is a people problem. And I'll draw an analogy because the problems don't change, right? Like the specifics of the problem change, but the fundamental property of this being a people problem doesn't. I'm going to go a little off the rails here, but talk about Ukraine, right? So Ukraine today is horrible, right? This is a horrible story, and we're all horrified by the daily news, but it's not like it hasn't happened before, right? You could summarize that by saying there's a belligerent power airing old grievances of questionable veracity to justify an incursion into a sovereign state of strategic importance, and they're opposed by a bunch of this sort of complex network of allies that are simultaneously trying to figure out how to satisfy their roles and responsibilities as allies while also centrally looking out for their own self-interest. And I could have said that about any conflict in the past, right? 1939 before World War II, 1914 before World War I. You can go back to even 1783 or whatever it was, the Russo-Turkish War, which is the first time Russia annexed the Crimean Peninsula, in 1853, where they first lost it in the Crimean War. It's like the same problem over and over again, different actors, different boundaries, different abilities to wreak havoc. But in the end, it's a bunch of people with competing interests and competing constraints or different constraints. They're trying to sort out their differences. And they're trying to figure out, can we do this collaboratively, or are we going to do it belligerently? And in this case, they've decided to do so belligerently. Well, back on the rails, I don't see any fundamental difference between that problem and an environmental problem. Same thing, right? There's a bunch of people, they have differing goals, they have different constraints, and we have a central resource, let's say water, and we're trying to figure out how to partition up the quantity and quality of that water while everybody gets what they need. And we can do it collaboratively, or we can do it belligerently. So, and none of them, nobody wants to do it belligerently, right? I mean, like that doesn't help anybody. Like, maybe there's somebody who'd like to do it belligerently. Are there lawyers in the room? They're the only ones who benefit from a belligerent process, right? I mean, the rest of us all suffer for it. You know, and we just went, you know, but we went all the way to Supreme Court and lost, right? And so nothing ended up, there was no benefit, like nothing actually changed out of that. We just ended up sort of getting stalled with the status quo after years of litigation. Didn't help, right? It didn't solve your problems. It didn't even substantively contribute to a resolution of it. It just sort of kept them in limbo for many years, and now we stare at the same landscape, no change. So if you think about it from a collaborative standpoint, like I spend a lot of time traveling around the state. My wife Kai can attest to the fact that how infrequently I'm actually home. I talk to a lot of stakeholders, and everybody, it turns out, wants the same things. Right? They all want healthy economies, they want healthy communities, they want a healthy environment. Doesn't matter who I'm talking to. If there aren't lobbyists in Tallahassee that are pounding the table and extolling the benefits of poor water quality, more severe harmful algal blooms, like that's not a thing, right? That nobody wants that, and nobody wants to be blamed for it either. So that implies there's like a policy space where we can have conversations and work towards common resolutions to common problems. But how do you have that conversation, right? So if like who hosts it, and who hosts it, especially in our most contentious and sensitive places like Apalachicola, like who's actually the person here that's going to host that conversation? Well, it can't be the regulatory authority or the regulated community. There's power imbalances there. There's uncertain motivations. There might be a lack of trust. So it can't sort of be sort of the state, or and it can't be the industry. It can't be the NGOs necessarily. You're looking for some safe space where you can have that conversation. And that's the role I think that NERRS can play. And I think they can play a central role in being the sort of nonpartisan, non-regulatory, certainly part of the state and federal system, but in a non-regulatory, non-threatening way, right? It's just a place where the feds and the state and stakeholders can all come together. And when you do that, then every stakeholder is co-equal, the regulated and the regulatory. Could be just co-equal participants in that conversation in a non-threatening place where we can talk about our common goals. and try to solve those common goals. And I have experiences with this in two ways, as Jenna just said. So when I first took this job, I started traveling around the state meeting the NERRS around our state. People knew who I was because I've been working with Catch Meg Bay National Estuary Research Reserve since 2006, I think. We've been there continuously. We've worked with them for years and years and years. We've hosted hauling scholars. We've got master's and PhD students work up there. Over the course of the 15 plus years, we've had an opportunity to really change the conversation up there. When we first got up there, we were interested in where were juvenile salmon using the landscape. We were doing the early electrofishing up in the headwaters and finding out that pretty much if you looked for them, you found them. People were like, whoa, we had no idea that these little streams that were 30 centimeters wide and 10 centimeters deep were chock full of salmonids. Like, how did they get there? How do they overwinter there? Because these are coho, they have to overwinter at least 1 year. And they're badly behaved, sometimes they'll overwinter too. Well, it turns out we learned that it's groundwater discharge, which comes out of the ground at a continuous temperature year round, keeps these tiny streams liquid all winter long. And so the juvenile salmonids can overwinter in these really small spaces where they're safe from freezing to death because of the groundwater, and they're safe from being eaten to death because they're not in the bigger rivers. So here we are, 15 years later, and that's the whole conversation on the Kenai Peninsula lowlands now. Everybody wants to talk about groundwater. Why? Not because of anything we did. I mean, that's the science, but it was KB NERR who were sort of plugged into that community. They were the safe space where they have, and you can imagine, like we'd like to talk about that area as a low regulatory environment. I mean, it's like, you're from the outside, you're not trusted, the government's not trusted. The authority is really the community. So then there's a lot of very interesting beliefs in the community, but there's this place where they can all come together and talk, and we can be part of that conversation. And people have decided that, wow, groundwater is this really limited, turns out, resource, and it's really crucial because not only is it discharging to the streams to keep those streams liquid and allowing their salmonid populations to persist, but they're all tapping into the same aquifers in their homes and pulling water out of the ground from the same aquifer that feeds the spring, seeps and springs. So suddenly everybody's really interested in talking about groundwater, and they're talking about it, right? Nobody had to come in from the outside with the regulatory hammer and beat them with it. They themselves want to solve that problem. And they want to do it because the NERR provided that space. And I think the NERRS, therefore now, and I'm speaking from a different perspective as the chief science officer, I see the NERRS in this state as playing centrally that same role. Like, here we are in the Apalachicola, like, where is there more complicated problems than here? There's a transboundary problem here too, which makes it even more complicated still. And I think the NERRS then can provide that safe space where that conversation can happen. But crucially, that conversation has to be based on like facts, right? It needs to have like sort of a scientific foundation. The science doesn't drive decision making directly, but it certainly provides that sort of framework. Like, that's the universe. Like, let's have a conversation at least within that universe. And that's another crucial role that the NERRS can play. They provide that role of sort of building that scientific foundation, annually updating it. Sharing it with the community and guiding or putting like maybe the guardrails on that conversation. This is the universe that we're going to talk about, because in the end, again, we all want the same things, right? Healthy economies, healthy communities, healthy environments. And that starts with understanding that healthy environment. So I'm pretty excited that you guys are having this. I apologize because I'm not going to be able to stay for the entire 2 days. I have to leave this afternoon. But I'm looking forward to hearing the talks this morning and looking forward to catching up with you guys afterwards to hear about how it all went in the end. So I'll leave with that. Thank you guys for what you do. And yeah, I'm looking forward to hearing the talks this morning anyway. Yeah. Oh, question? Sure.
Okay.
And Bruce, I'm going to go ahead and unmute you. You can unmute yourself now if you'd like to ask a question. Well, if you have your question, still type it into the question box. That's it later. Thank you.
All right.
Good morning, everybody. My name is Jason Garwood, and I'm the research coordinator here at the Apalachicola National Estuary Research Reserve. And it's my honor and pleasure to introduce the first talk, as well as a friend and colleague of mine, Dr. Christopher Anderson of Auburn University, who is going to be talking to us about spatial and temporal patterns of tidal freshwater forested wetlands along the lower Apalachicola River system. And with that, we'll let you take it away, Chris.
Yeah, thanks, Jay, for the for the invitation and for the introduction there. Really appreciate being a part of the symposium today, and I wish I could be there in person. I was just down there actually about a week ago. But for my talk today, I want to talk a little bit about tidal freshwater forested wetlands, and I wanted to kind of get an opportunity, I guess, to give a little bit of an overview of some work that we've been doing there. I've been involved with the NERR going back since I started at Auburn, so we're talking about 15 years. And so off and on, we've been doing work looking at the tidal freshwater forested wetlands. I want to mention real quickly too that I work with a couple folks, particularly Sam and Jason there at Apalachicola. I put them here on the title screen too. And more recently, I've been working with a couple folks at Auburn, including Ian Davis, a graduate student, and Lana Ryan, who's a professor, along with me at the College of Forestry, Wildlife, and Environment at Auburn. Okay. So yeah, if you are in Apalachicola Bay and you travel up the river or one of the many distributary rivers, as you go up the river, you'll see a lot of those rivers are lined by tidal marshes, but it doesn't take too long before you will start to encounter the tree lines and the transition zone going from marshes to the tidal forested wetlands. And so the bottom panel there, you should be able to see an approximate tree line. The map on the right I like, it actually comes from a Florida Fish and Wildlife Commission brochure for the area. The orange there being the marsh, and then the gray being the river swamps that occupy the lower Apalachicola River system there. So just orient you, we're kind of just off the screen here in Apalachicola. You got the main stem river, but a lot of this area that we see, particularly if we look at this one map, the color map here, a lot of that gray area we've found is pretty much influenced to some degree by the tides, by tidal influence, although that it is still primarily freshwater given the influence of the river. If you go into one of these swamps, you might see something that looks like this. And so these freshwater forested wetlands are a little different than the types of swamps we see further up the river that are more river dominated. The ones down closer to the bay tend to be flooded more frequently. The floods are tidal, so they're not as substantial in terms of depth, but the duration of flooding can be much more substantial. They're not as dependent upon the river flows and river stage for flooding to occur. They do periodically get some saltwater intrusion, and that's a particularly important issue when we think about these in the future of these swamps. But most of the time, they're occupied by relatively fresh water, again, by the influence of the river system. The swamps themselves look a lot like this many times. You'll notice a lot of understory vegetation here, and the trees are typically smaller than the ones we see further up the river in the non-tidal parts of the river. The smaller stature trees allow more light, allows that understory vegetation to occur in there. Another feature that's interesting is if you look on the one on the left in particular, you can see there's sort of a high ground, relatively speaking, where some of those trees are, and then the flooded part, there's sort of what we call a hummock hollow type of topography in there. So we've been looking at these wetlands for some time. Our overarching goals are really to kind of better understand how tidal connectivity influences these types of wetlands. And then using that information, we're very interested in figuring out the vulnerability of tidal forested wetlands in this river and other rivers and how that relates particularly to river flow and tidal connectivity. So that can relate to, again, river management and flow regimes, but also certainly sea level rise. The trees in this area do have some tolerances to brackish water, but as salinity starts to increase, the expectation is that some of these areas will transition to marshes. And a third sort of research goal that we have is to better understand the functional role of these tidal swamps and how they connect to the bay. So mostly what I want to talk about today, though, is the compilation of a lot of forest survey work that we've done and sort of understanding how tidal conditions influence the forest communities in this part of the river system. So I've got that same map up here on the top right to give you some reference. But this more complete map in terms of all the tributary and distributary rivers, you can see that since 2007, when we started doing some work out here, we've had over 35 opportunities to establish or conduct a forest survey. And these forest surveys have been done to really to better characterize the communities that we have in the lower river system and begin to understand how factors such as tidal influence and salinity might be shaping these areas. So a lot of this work has been done sort of incrementally. It's not been done continuously. But where we've done forest survey work, we typically use the same protocol. Have forest plots that are 500 meters squared, circular plots that are established roughly 60 meters perpendicular from the nearest river. We do have some sites that were on that map that have more than 3 plots, but all the data I'm going to show today relates to this plot that is in the same proximity to the nearest river. So for these circular plots, we identify the trees, tree species. Trees in this case are trees that have a diameter at basal height of more than equal to or more than 5 centimeters. And we use that data and for a few ways, but for today's talk, I want to talk about importance values of tree species. And so when we have a complete plot surveyed, we know all the trees and all their diameters, we can calculate, first off, its species relative density. So the portion of all the trees that belong to that one species, we multiply that portion by 100 and get a relative density score. And then we do the same thing with its basal area. So looking at the basal area of those trees and how much each species occupies of the relative basal area, we get a relative dominance score. And we add those two things together to get an importance value that if you aggregate all the trees or all the species together would equal 200 in this case. In many plots, we also do other measures, particularly related to vegetation. I'll talk a little bit about shrub counts, so the smaller trees that are basal height, and understory cover as well. So some of our first work was done starting back in 2007, and we were out there for about 3 years. And so all the sites with a star were some of our initial sites, and we used water level monitoring stations to gauge some of the hydrology related to these tidal swamps. And I should mention we did some non-tidal work too. So off this map, if you go, one of the furthest up here is on the Apalachicola River. Those are a little further into the non-tidal part. So I'm just showing the tidal wetlands here. A lot of these that we initially started were in the lower section, and we started working with the NERR to get into, I should say, the interior sites that I have listed here. But the product of that work was that we found very discernible community differences between tidal and non-tidal wetlands. And our tidal wetlands is sort of represented in this cluster analysis. You know, species like swamp tupelo and bald cypress clearly aligned and were more prominent in these tidal wetlands. And then as you get further up the river, other species common to the Appalachia, like Ogeechee tupelo, water tupelo, those were a little more restricted to the non-tidal parts. So we sort of identified these important species to our tidal wetlands. Starting in 2015, we focused a little more on the East River and St. Mark's River and sort of focused on the tidal part of it. again, using a combination of forest surveys and water level and salinity data in this case, we were able to develop some models that looked at long-term mean daily salinity in these two river reaches. And what we found is that if you aggregate the tidal and non-tidal species, that they do tend to separate across this tidal gradient, and that in most cases, when you got above a value of 0.2 parts per thousand on average over this 30-year average, those tidal species became much more important than the non-tidal. So this area, where it's less than 0.2 parts per thousand, you get a pretty good mix. It's really kind of a transitional zone from tidal to non-tidal. And now, kind of coming up to sort of more of our recent work, we've actually, working with the Apalachicola NERR, started to remeasure some of these forested areas that we did back in 2010, or 2007 to 2010. So the sites you have mentioned on or shown on here are ones that we remeasured. These were all stations where we tag the trees, so we actually go back and remeasure those trees and see how they progressed in over 10 years. We did add a couple more sites along with some more permanent water level and salinity gauges that folks at the NERR are monitoring and managing. So to highlight what we found, really the big takeaway was the amount of shrub density that increased in these tidal swamps. So this is numbers of shrubs per hectare. Between our 2007 and 2021, it's a substantial difference in increase in almost all of them, except for one. And we suspect this might have something to do with the Hurricane Michael, because we did see, in addition to some moderate understory cover, we did see the loss of some canopy trees in that area, but it wasn't substantial, and there wasn't big differences in terms of tree density and basal area numbers between the 2 years, and we didn't see any particular trends related to the importance values or any species that was particularly changing. There was a lot of variation there. Having this updated data, I wanted to, for this talk, kind of take an opportunity to sort of put together some comprehensive maps and just sort of show where some of these important species occur in their distribution. So using all that data, and again, some of it's a little older, but it is, it is from based on our recent remeasurements, I think still viable to look at sort of the relative distribution across this area. And we see swamp tupelo, for instance, as being a particularly important tree species, the lower tidal swamps there. Again, you sort of see the reds and the oranges here where it's particularly prominent in terms of its importance values. And it's pretty well distributed within the tidal reaches here, including even some of the tributaries off the Appalachia. We talk about flows coming into Jackson River. Bald cypress was another sort of indicator species of tidal swamps. And again, maybe a little more, the yellow dots and less of the orange and reds here, but again, another really particularly important species. And ones, if you look, where it does occur in real abundance, at least in this tidal reach, tends to be on the river reaches closer to the bay. So some indication maybe that there's a preferential habitat there for those tree species. We're really interested in cabbage palm as well. And cabbage palm was an indicator species from our previous work as well. And you can see that it is sort of a hit and miss. We've seen areas where it's really thick, and particularly in some of the lower tidal reaches of the East River and St. Mark's. My student Ian has been looking at this a little closer with some remote sensing. Cabbage palm really shows up well in nape imagery, and so using that, some NDVI data, she's been able to really hone in on the range of cabbage palm. And so you see that red blotch in the middle there. That's really removed from our sampling area, but it's clearly sort of a hotspot area for cabbage palm and the forest in there. It's an area too that we suspect is going to have a little higher salinity because it doesn't have as much of that freshwater influence coming down those distributary rivers. It's sort of a little more of an area in between those influences. So definitely an area I'd like to see and look at more. And it's a reminder that we don't have really a complete survey of these tidal swamps at this point. There's some other factors that I'll mention that influence these trees as well, in the tree species. In the past, we're starting to do again some relative elevation work. And so I mentioned at the beginning that these tidal swamps oftentimes have a hummock hollow topography or microtopography related to them. And so taking relative elevations, we calculate a coefficient of variation of those relative elevations. And what we see is that when we have a lower CV or variation, it tends to promote more of the swamp tupelo, but that swamp tupelo seems to decline as we get into a higher coefficient variation, meaning, or how we're interpreting it, is that when we have more of these hummocky areas, it provides more relief for some other tree species. And we see less of the swamp tupelo, get more hardwoods and our cabbage palm perhaps in some of these kind of plots. So topography, microtopography, and elevation, we think, play an important role. We see some somewhat similar trends related to cypress as well. So again, sort of another factor that contributes to the variation that we see out there. So to kind of wrap it up, our remeasurements from 10 years plus of tree data shows that in terms of the canopy and canopy trees, there was some changes in certain plots, but largely the biggest change was an increase in shrub density, small tree density. Again, we suspect this has something to do with Hurricane Michael that came through in 2018. We have through the years sort of determined that there's certainly a lot of complexity when we talk about the various factors that are influencing these swamps, but salinity, microtopography, relative elevation, all of these things contribute to a lot of the species composition that we see out there. And this work is again supporting other and future work that we hope to do, looking at sort of making the connection, both in terms of maybe the export of material and nutrients and things like that from this part of the river system, this tidal forested part in Apalachicola Bay. We suspect that there's some potentially seasonal importance to maybe bay productivity down there. And so with that, I'll just quickly acknowledge a whole host of folks and some that I probably haven't met yet that have been out and sort of contributed to some of this. Ted Kessler was somebody that we have worked with in the past, and he was responsible for the understory and shrub data that was collected more recently. And then I do want to acknowledge our funding sources, Florida DEP and Apalachicola NERR, along with the USDA McIntyre-Stennis Forestry Program for supporting this work. And hopefully I'm not too much over time, but if I have time, I'm happy to take any questions.
First of all, great talk. I was really interested in your plot of the importance value by salinity. This is by Mark Rains, by the way.
Yeah.
And I was struck by the abrupt transition threshold at such a low salinity. I mean, I could survive off water, drinking water, almost an order of magnitude higher than that salinity. So do you have thoughts on what drives such an abrupt transition at such a low salinity? It's like, what's even happening?
So the figure where you see the transition in tree species related to the long-term salinity average and what contributes to that abrupt. Yeah, so that was some interesting work, and when we focused on those two river systems, and there was some differences between the East River and the St. Mark's system there. The St. Mark's in particular had a very abrupt shift in salinity, and it was more saline on average near the outlet, near the lower reaches of it. The East River, though, I've been thinking about a lot, and you know, that was a little more moderate in its salinity, and I think the vegetation supported that. There, if you think about the East River, it's sort of on the edge of that river delta area, and it does have outside influences. So in addition to what's coming down the Apalachicola River system itself, Graham Creek, for instance, flows into that. And so we think we see a signature and maybe a moderation of some of the salinity there related to that, you know, some of those peripheral waters that are coming into the delta system there. So yeah, I'm not sure if I'm getting at your question exactly, but there's There is some, abrupt shifts that probably, in addition to those factors, we think about sort of elevation playing probably an important role here too in tidal reach.
Yeah, we're probably running out of time. Oh, okay, so let me ask a follow-up, Christopher. So is that long-term salinity average driven, I mean, is that a pretty steady salinity, or are these episodes, are these overwashed episodes that create the impression of above 0.2, but actually what might be happening is that those are places that flood during storm surge periodically, and that knocks certain species out? If that makes any sense.
Yeah.
Is it a high salinity excursion, or is it the chronic differences in salinity that drives that?
Yeah, the dynamic and the differences are primarily driven by, their response to variation in river flows. So there's sort of two things that we see kind of causing salt water to move up further up the river. And so we do see these episodes where we have, tropical storms and tidal surges related to storm events. And those tend to be fairly brief, at least what, the data that we've actually captured by, being out there during one of these storm events. But the incursions that we get when we have low river flows, and then you have, high tidal events. I've been working a little bit, started to work with some of this data to look at sort of the characterization of those type of events. And those are where, we do get, oftentimes repeated days of saltwater exposure into these sort of lower forested wetlands. And, in terms of its contribution to that average, that's probably going to be the biggest contributor as far as driving those different averages. Yeah, the modeling part of what we did on that project was it was one of these kind of machine learning exercises. So it's a little bit of a black box that allowed us to generate daily averages. But the actual data we collected to support and build that was, we saw these kind of events where, again, the combination of low river flows and then, you get your sort of higher spring tide type conditions. That's what really kind of drove the salinities in these parts.
Thanks.
All right, thanks, Dr. Anderson. With that, we will encourage folks to hit the Padlet if they have any other questions or comments to make, and then we'll move on to our next talk. So next we have John Tracy from the University of Florida, who's going to talk about from the bottom up, the first year growth of 5 floodplain tree species in a controlled moisture regime experiment to assess cause behind shifting Apalachicola floodplain forests. And with that, take it away, John.
Thank you very much. Awesome. Nice to meet everybody. John Tracy. I am a PhD candidate at the University of Florida, and I'm particularly interested in floodplain forest ecology. I would consider myself a floodplain forest ecologist at this point, but I consider myself a perpetual student of floodplain forest ecology, so always learning something and really enjoying the process. My research is funded by a grant that was granted to the Apalachicola Riverkeeper Organization by the National Fish and Wildlife Federation. And so we're part of a multidiscipline effort, slough restoration effort aimed at trying to improve slough connectivity throughout the Apalachicola River floodplain and improve the ecology of floodplain forests that we believe have been degraded over the past several decades by anthropogenic impacts and climatic impacts. Let's see. All right, so I'll be talking to you today about a controlled moisture regime experiment that I decided to come up with to test the tolerances of 5 different floodplain tree species in their earliest life stage, from sprouting as a seed through their first year of growth. So let's talk about why I decided to do this. And to do that, we'll go through a series of images and talk about floodplain ecology up in the non-tidal reach of the floodplain. So it was great. I'm so excited that I got to follow Dr. Christopher because he covered ecology about the tidal reach of the floodplain. And my work kind of focuses on the non-tidal reach where everything is impacted by the flow from the river and all of the influences of anthropogenic forces, whether it's agriculture or dams or municipal pulls for water on the river system from upstream, it all affects the Apalachicola floodplain forest beyond the non-tidal reach. So in this first image, what I want you to look at is take a look at all the different characteristics that you see here. Obviously, lots of water, a very closed, dominant canopy, a mature forest, plenty of shade on the ground, little hints of sunlight here and there. But as you look at this cypress tree in the foreground, I want you to think about what adaptations it has to survive an environment like this. What requirements did it have to germinate as a seed and grow tall enough to get above these floodwaters so that one day it might have the chance to climb up and become one of those dominant tree species. In this next picture, this was taken very near to where the other picture was taken. Very similar environment, but in this picture we see a dominance of water tupelo. These are these swell butt trees, very dominant in the canopy. We also see some bald cypress as well. This is a mature stand here. Notice a lot of shade, not too dense of a mid-story canopy here. And vegetation on the ground is even limited by the frequency and long duration of flooding that happens at this elevation. Moving on to this next image, you'll notice that there's a little bit more opening in the canopy. This is from damage from Hurricane Michael. You'll notice there's less water on the ground, a lot more vegetation, a little more dense. The microtopography that Dr. Christopher talked about is also different here. There's a little bit more of a slough, a hummock hollow characteristic that he had described. And so what you see here is even a more dense mid-story. And so canopy dynamics are very much so impacting what you see here. There's a little bit more light coming through. It's allowing different species in this drier environment to kind of climb up and fill in this mid-story. Now in this last picture, notice how much more dense it is. You can't see quite as far as you could in that first image. There's a lot more dense of a mid-story canopy. Some of these smaller trees, oh, perfect, this works, are able to climb up into the mid-story and create a lot of competition for whatever trees are trying to grow down here on the bottom. And so what I'm trying to point out here is the commonality between all of those four different images was that they all are dominated by cypress tupelo in the overstory. And so this is a plot here where I've been taking some measurements similar to like Dr. Christopher had been doing, and I have noticed that the mid-story canopy is now dominated by species that aren't represented in the overstory. And what that means is that microtopography and other variables are impacting the ability of the species represented in the overstory to germinate and survive and eventually climb their way up to the mid-story and then into the canopy dominance in the overstory. So this is very important because over the years, the USGS has been monitoring forest composition throughout the entire floodplain, and they've been noticing forest composition changes in the non-tidal reaches. We've been noticing that swamp species like tupelo and cypress have been declining in density significantly. They noticed this between 1976 and 2004. The species of most concern were water tupelo, Ogeechee tupelo, which is important to the tupelo honey trade around here, and then potash. And so when I first learned these characteristics of this floodplain and this issue of species composition changes, I was trying to figure out how I can best figure out what is driving this change. And so there's many different factors. It could be the altered flood regime, it could be climate, it could be gap dynamics, canopy structure, shade tolerance of the different species, and flood tolerance of the different species. And the reality is that it's all of those different things combined. But I wanted to start testing which ones had the most influence, what's really driving all this change. And so I decided to start with testing flood tolerance of these different species. And I wanted to start from the bottom up in their earliest life stage as seeds into their first year growth as seedlings. So I developed an experiment where I would test them in various different moisture regime treatments throughout one growing season. We went out to the floodplain and we collected about 10,000 seeds of the 5 different species Two of them being two tupelos, which is Nyssa aquatica, which is water tupelo, Nyssa ogeechii, which is ogeechii tupelo, the ash species, which is Carolina ash or pop ash, and then overcup oak and water hickory. And in order to get the degrees of freedom and repetition that I needed to have significant results, I wanted to repeat this 5 times. I had 25 individuals in each treatment and 12 different treatments, so it came out to about 7,500 individuals. And so I planted them in each seed in individual 1-gallon bags with about 6 to 8 inches of soil. And then I put different levels of moisture in each box that I lined with plastic and maintained those levels of moisture throughout the year. The different treatments I had involved different variations of moisture deficit and then saturation, where saturation meant that I added about 3 inches of water up from the bottom of the bag. They kept all the soil saturated. And then flood meant I put about 3 inches of water over the top of the soil. And this is going to have different variations and effects on the seedlings. I wasn't able to control completely for moisture in terms of precipitation, but I thought that was okay because I wanted to more simulate what these trees are going to experience in a typical year. I wish I could tell you about all of these treatments and results, but today we're going to focus on treatment 4, which was perpetual moisture deficit throughout the experiment period, and then perpetual saturation throughout the experiment period. So treatment 10 and treatment 4. Let's see. Something I wanted to mention about these different species is that the competing species, these are 2 species that we believe are moving into these swamp environments as they're becoming drier from altered flood regimes. They are heavier seeded species, meaning they have a lot of stored carbohydrates in their seed that allows them to establish an extensive root system and then put up a shoot. Another advantage of this is that if something happens, a disturbance that kills off this shoot, it can die back to the seed and still have enough stored carbohydrates here to put up another shoot after a disturbance. That's something to note that gives these species quite a bit of an advantage over these swamp species here. These are lighter seeded species here on the right between the ash and tupelo, where they have to put up a shoot and start putting out leaves, start photosynthesizing, creating energy, and then building those carbohydrates to build an extensive root system. So if something happens early on in their life stage to damage this top shoot, that's kind of it for them. They don't really have enough stored carbohydrates to shoot up to recover. And so that again is another reason to consider with this experiment of an adaptation they have and an advantage they have out in the floodplain. This is the temperature that these seedlings experienced during the experiment period last year, which was from May 10th to November 10th. That's the typical growing season in the Apalachicola floodplain. We had some high temperatures in the summer that caused some mortality events. We also had some dry fronts that came through last year in the earlier part of the winter and fall months that created some very dry soil moisture measurements for some of these seedlings and had some really interesting effects on the different species. So keep this in mind as we go through some of these summary statistics from the experiment so far. I haven't been able to dig into it too far with good statistics looking at significance, but we can look at some basic summary statistics. So again, we're looking at perpetual saturation, so having about 3 inches of water up the soil gradient, and then also treatment 4, which was perpetual moisture deficit throughout the period. This is a look at the moisture percentages that were in the different treatment blocks throughout the period of the experiment. Notice that I had good separation between the saturated treatment and the dry treatment here. Remember, I talked about those dry fronts later on in the experiment that brought moisture percentage way down for those that were in the moisture deficit treatment here. So looking at average germination, and this is in terms of individuals. There were 25 individuals in each treatment. I'm only able to consider 2 replications at this point. I'm still entering data for the other 5,000 data points, but I expect these results to become more robust based on my observations. But the most important thing I wanted to note in these 2 figures here is that between the saturated treatment and the dry treatment, overcup oak, one of the competing hardwoods that we believe is moving into the swamp environments, had a much higher ability of germinating in the dry treatment than it did in the saturated treatment. Another thing to note when we look at the time scale across the experiment period, the heavier seeded species of overcup and water hickory had much more delayed timing of germination rather than the lighter species that germinated very quickly in the first few weeks of the experiment. And there's different conclusions you can have with this data. Remember, we talked about how the lighter seeded species don't have those stored carbohydrates to recover from disturbance or dieback or anything like that. When you germinate that early in the season and say another flood comes in kind of early in the season, overtops their terminal bud and kills them, their chance of recovering in that area with that seed lot is limited. But these heavier seeded species have the chance that if some of these die by a later flood event, they have other individuals that are going to germinate later in the season in a saturated environment. We noticed that this timing is a little bit more shortened in the drier environment, but still the heavier seeded species have a bit of an advantage here in timing. Remember when I talked about the higher temperatures early on in the experiment period, it knocked out a good bit of the seed lot for some of the lighter species. And so that kind of gives us a conclusion of their inability to compete with some of these heavier seeded species when there's disturbance early on in the season. Here we're looking at average mortality between the individuals. Let's see, in the saturated treatment, it makes sense. It was kind of ideal conditions for some of these species. There wasn't a whole lot of mortality. They had plenty of water. Let's see, we'll go back here. Again, mortality was very high early on in the season for the lighter species. And then later on in the season, when we got the very dry soil moisture, water hickory seemed to have the most mortality in relation to that disturbance. Let's see, mortality was also fairly high for water tupelo compared to the other tupelos or the other lighter seeded, or all of the other species in general. Now, let's see, so this is looking at cause, and this kind of explains what I was just talking about. Early on in the season, we had a heat stress event where a lot of the seeds got scorched when they were very young. And so the lighter seeded species responded most poorly to that event. Moisture stress later on in the season ended up affecting water hickory the most. So I took measurements of height 3 different times throughout the experiment. Once at about 6 weeks, again at about week 14, and then again at week 27. And so this represents the first cycle. And what we can notice here, what I really wanted to point out was notice how quickly overcup jumps up in height in some of the earliest weeks of development. So this represents a 5-year-old seedling here in this column. And they were putting on almost over 15 inches of height here during that time period. And so what that makes me think about is, okay, if their germination is delayed later in the season and they have a shorter growing season to grow tall enough to get above floodwaters, overcup might have a bit of an advantage there by germinating later in the season compared to these other species. Let's see. So this would have been taken midway through the experiment. This is where we start to notice that delay in germination. We have a bunch of different age groups of the heavier seeded species here, whereas all the lighter seeded species have are all older age groups for these seeds because they didn't have anything that germinated later in the season. What is important to notice here is that notice that the tupelos are starting to put on a good bit of height here and compete more in height with these heavier seeded species. In terms of the saturated treatment, it does seem that different individuals had different reactions to saturated soils compared to the drier treatment. And then this would have been at the end, the very final measurements in terms of height, average height. Again, tupelos seem to do very well in the dry treatment in comparison to the saturated treatment. And what's interesting about this is that there's research from 50s, 60s, and 70s, why for some reason they were interested in tupelos back then. And some of that research suggested that tupelos prefer and grow best, are most productive in saturated soil environments. And what I've been finding is that's not necessarily the case. I think they do just fine in dry environments. They have kind of a different tolerance and ability to compete with these heavier seeded species. But what this made me think of is that the issues with declining density of tupelos in the floodplain isn't so much related to their ability to survive in drier conditions due to altered regimes, but more so about canopy dynamics and allowing these competing species to move in, take over the mid-story, and then shade them out. And so the conclusions I have from this experiment so far are driving me to want to do more experiments testing these species in terms of shade tolerance and learning what their ability is to compete with all of these other species that are moving into these lower swamp environments. And I think it's going to point us in the right direction of figuring out how these changes in forest composition are affecting nutrient fluxes laterally and downstream in the floodplain and out to the bay. And hopefully that'll help us figure out what are the ecosystem services that we might be losing by having these swamp environments shrinking over time. So I hope you found that insightful. Please keep an eye out. I'm going to be working on the rest of these results for a while now and doing more presentations and hopefully some really good publications. I like to talk about all of it on Instagram and Twitter, so check me out there and check out the forestry lab, Dr. Sharma's forestry lab. Many thanks to all the lab members we had. It took a lot of hands to put this idea in motion. So thanks for having me.
What was your treatment water source?
It's well water that we had on campus. Yeah, I had a couple questions about that when I shared it on social media. They're like, did you use municipal water? You know, because there's all these added elements. And no, it was all well water that we have on campus in Milton. Yes, there were some limitations to this experiment. Like I wanted to use the soil type that you would find, like alluvial soils that you would find in the floodplain, but in floodplain soil types are kind of limited here in Florida as compared to back home in Louisiana. It's a lot of heavier clays there, so they're protected, and I couldn't grab any alluvial soils. But I did do an experiment to find out what soil type I could get that retained moisture almost for as long a period as floodplain soils do. So I got as close as I could.
I don't know.
Yeah.
How did you determine if things had germinated or died? Did you dig them up, or were you just looking at what emerged from them?
Yes, I was monitoring them almost every day out there, watching for when they would put up their first shoot. So yeah, timing was more about, yeah, there's questions over when do you actually consider what's germination or not, but I couldn't do any destructive sampling or anything like this if I was going to do height. So it was mainly on when they put up their first shoot. So I could tell when the seed had broken, and at least like for the heavier seeded species, they started developing roots first, and I could tell when that was happening. So I had tags and I would mark what week that they germinated in. And then when they died, it was pretty obvious. You learn when you spend more time out there how to tell whether they're dead or not based on how rigid they are, and then you can kind of scratch the side of them and see if they're still green or not.
Do they germinate on the surface, or are they buried?
They're buried a little bit, but a lot of them over time, they weren't that deep to where I could dig out a little bit and see if they had started or not.
So were you had so many of those buckets. Were you monitoring soil moisture individually with each one of those? So that's...
Well, I would take 3 measurements across each treatment box. It would have been nice to have it in all of them, but I would do it manually and randomly across each box because I knew that they were all kept about the same moisture in each treatment. But no, I couldn't do each individual.
So they weren't growing big enough that you had to worry about the transpiration affecting soil moisture on a big plant versus a little guy.
Oh, right. Yeah. See, that's something I couldn't really equate for, unfortunately. It would have been nice, but I'd have to have that would take a lot more time. But no, that's a great point there. So yeah, the best I could do was take an average. Yeah.
I'm curious about what drives the idea of the treatment plants. Like, was there an idea that was thought about and why you chose those things?
Yes, it's the variability in the flood years each season in the floodplain. I looked at some of the past flood records and saw that, you know, sometimes you'd have a flooding throughout most of the year. Sometimes you'd have, you know, flooding would start in late summer and continue all the way through March of the next year. And so it's very variable. So I tried to make as many replications and variations as I could. So thank you all very much. Appreciate it.
Alrighty, so moving on to the third talk of the morning, we're going to hear from Dr. Steve Leitman from Apalachicola Bay Systems Initiative, and he's going to talk about defining metrics to enhance sustainability on the Apalachicola.
So good morning. I'm 2 years away from having my 50th anniversary working in this basin. And it's also special for me to be here because when I was a graduate student back in the 70s, I co-wrote the EIS that created the Estuary Research Reserve here. So seeing where it's gone is pretty awesome. So I'm going to go and step out to the whole basin, to the systems perspective from looking at individual projects, which has been very interesting. And we're going to talk about flow metrics. Okay. In talking about flow metrics, what I'm referring to is the volume of flow, which can be used to define acceptability of flows entering the estuary. And it is through the development of flow metrics that we're able to take modeling and evaluation stuff and translate it into ecology. And this is a really important thing that is often really overlooked. And by flow conditions, I'm referring to not just magnitude, but it covers the magnitude, duration, frequency, and timing of events entering both the estuary and the floodplain. And in developing metrics, consideration has to be given to the capacity of the system to actually provide water. So this is a little cartoon that I put together. And one of the anomalies that we have in this basin is that about 2/3 of our storage is located in the upper 10% of the Chattahoochee Basin. And the balance of the management storage is at two other reservoirs, which is West Point and Lake Eufaula or Walter F. George. Now there is a reservoir at the Florida border, Lake Seminole, which looks really big to us small humans. And the volume of water at full pool in that reservoir is 1 day's average flow in the river. And because of riverbed degradation during low flow, there's essentially no water in storage at the reservoir because of dam safety and head issues. So we have this funny situation where half the basin, being the Flint, has no storage capacity, and most of the basin in the Chattahoochee, most of it is up in the upper 10%, which means that our ability to manage flows in the Apalachicola Basin is not what most people think it is. Now, the Corps of Engineers about 4 or 5 years ago came out with what's called a water control manual. And what they did is that this is how much the reservoirs, and one of the big misunderstandings that people have about this manual is that the manual defines the volume of support from the reservoirs towards flow. It doesn't define the actual flow. And the reason for that is, as we were talking in the previous slide, if most of the storage is at Lake Lanier, then during droughts especially, Lake Lanier can get drawn down and there's no capacity to really do it. So if you have a lot of water coming down the Flint, there's nothing you can do but just let it pass through. And it's also not uncommon to see us in drought operations, and West Point and George are close to full. So Lake Lanier is driving what's happening with the whole management of the basin, and they're only providing 5,000, but 90% of the basin is providing inflow, and there's nowhere to put it but let it through to the Apalachicola. So when you see this 5,000 that people talk about, it is not uncommon to be in drought operations and have flows of 10, 15,000 in the Apalachicola. And so people really, I don't think, get the water control manual that well. So my intent in developing metrics was to understand how we should manage the basin in the future, not how we should manage it in the past. And when the Corps of Engineers developed their water control manual, they went through and looked at historical climate for 74 years, which sounds great. You know, wow, that's a lot of data, 74 years of daily data looking at how to manage it. But in fact, the 74 years is only one way those 74 years could have happened. And when you look at what's going on in California, when you look at what's going on in the Colorado Basin, when you look at what's going on in the Mississippi, relying on the past to say what's going to happen in the future is a real bad gamble. And you're asking for problems. And so the water control manual that we have is based on historic flows alone. And I have a paper in for publication that I did with a woman that was at the National Center for Atmospheric Research and a man in the engineering department at FSU, where we took 100 simulations through synthetic hydrology of the historic flow. We're not talking climate change, it's the same volume of water, but what we've done is vary the droughts, vary the floods. And so the duration, frequency, timing, everything has changed. And we said, how well does the water control manual work under different distributions of flow, under different variability of climate? And surprise, not that well. Who would have seen that coming, right? So I think in the future, we should expect flow events which are different than what we have in the historical record, and that we really need to develop our manuals to approach operations in these basins based on what we expect in the future, not what we saw in the past. That's just a bad gamble. So in developing performance measures, first of all, when I worked on the compact, and I was the person that did the modeling for the state of Florida when they were having the compact negotiations. And the compact, for those of you who don't know, is essentially it's a legal agreement. And the 3 states created the first compact of how to deal with managing water in the Southeast. And I was doing the modeling, and so I was told, well, come up with a better way to do it. And I'm sitting there going, you know, well, how do you define better? And they go, you do it. And I'm thinking, I don't think that's what I should be doing. I think, first of all, that your performance metrics of what you expect from a system should be, at a minimum, endorsed by stakeholders, and they should be involved in it. It should be measurable. It should be transparent. It should be subject to new information and understandings as they are developed. The sources of where the information comes from. It should address magnitude, frequency, timing, and duration. And it should be taken that if you have too many metrics, you become like a deer in the headlights. You can't make a decision. So if you have a list of a couple hundred metrics that you have to go through to look at something and say, this is what I call good, you'll never get there, in my opinion. So at present, I would say that we have not distinguished to an acceptable level of precision the volume of water needed to sustain the estuary and the floodplain over time. And an interesting question is, why haven't we got there? What has been the problem? If we need to define what we need, why haven't we done it? Anyone have an opinion? I think it's, one, it's complicated and difficult. And 2, it's a lot easier to develop a model and come out with numbers than it is to say what those numbers mean, unfortunately. So some performance metrics have been developed. The ACF stakeholders, in the process of developing a sustainable water management plan, came up with a whole series of metrics. And it was a large list, and I personally don't think I could use those to make a decision what's the best way to manage the basin. It was a good start, but it had a lot more to go. The Corps of Engineers selected the preferred alternative for the water control manual based on a set of metrics. And for years, I taught a class at FSU, and if one of my students came up with the metrics of the quality that the Corps did, I would flunk them. Hard grader, I guess. And then the Fish and Wildlife Service, in a biological opinion, also developed some metrics. And one of the things that we should understand that the water control manual does not include the Apalachicola Estuary. The Corps of Engineers, the ACF basin was originally developed mostly for navigation purposes. And so the Gulf Intercoastal Waterway runs through Apalachicola Bay, and the ACF project starts up in Columbus, Georgia, Bainbridge, Georgia, and comes down to Apalachicola. So they divided it into two projects. And when they developed the water control manual, the water needs of the Apalachicola Estuary was not part of the calculus in selecting preferred alternative. Are they connected? Absolutely. It's a horrible thing that they did wrong. And I would hope we could change that in the future. I think Jen agrees. Then, when we went into the ACF compact, we went through years of negotiating with the states of Georgia and Alabama, and then we went through the Supreme Court lawsuit. Florida said we want more water, but defining how much more water we wanted was never done and has never been done. And that didn't work. And so in the lawsuit, we lost because, in my opinion, we really couldn't say what we wanted. The court agreed that there had been damage, but to pin the damage on Georgia or to say exactly what we needed and how it could be done better, couldn't be done. And one of the ironies of the lawsuit is that we focused on demands mostly. And I'm not sure what all the logic was, but we didn't get into saying that it's how you manage the water and demands. Okay, I have 1 minute, so I can pick up.
It's flexible questions.
Okay, so performance metrics are being developed under the Apalachicola Bay Systems Initiative and in the Slough Restorations Project. And real quickly, as I've been working with Ken Jones and with John's work, and we actually went through and looked at, was it possible in dealing with those long droughts and long periods of dryness in the floodplains, was it possible to provide freshets to flood the floodplain, and then how much it was within the capacity of the system? Did we have enough water in the reservoir to do it without trashing the reservoirs, and at the same time help them? And surprise, you actually could. And then we are looking to try and do a similar thing for the estuary, but more work has to be done to get good numbers for that. And so an example of performance metrics for the capacity of reservoir support would be the volume of water in the reservoirs. We need to find what's a safe thing if you don't run out of water. Because if you have no capacity, you're at complete whim of climate. For the estuary, it could be flows necessary to provide favorable salinity during the seasons of oyster larval transport, and a lot of other ones we could come up with. And an example of a metric could be the volume, timing, and duration of flooding events. And I will say that in developing the biological opinion, I worked on that with Fish and Wildlife Service. That's why I like those metrics. And they could only deal with endangered species, but in looking at the mussel life cycle, it dealt with the flooding of the floodplain. So part of what was required for the Corps in evaluating and in dealing with this preferred alternative is they had to deal with floodplain inundation because it was tied to the flooding of the floodplain, which was tied to an endangered species by the Fish and Wildlife Service, which I thought was a good move. So questions that we have is that what is the process used to develop metrics, which I think is similar to the question we had earlier of what do we do from here. And how do we get such a process to be seriously attempted? And are there any other questions? Yes.
Is it every 10 years the water control manuals reevaluated, or how?
It's written in there that every 5 years it's supposed to be reevaluated.
So it should be coming up.
It should be coming up very soon. And I've been talking with I work both for ABSI and I work on contract with U.S. Fish and Wildlife Service. I had many years ago when they were first developing one of their biological opinions, I was at a conference and went for a walk with gin and tonics, they always help. And went for a walk with the head of the two offices and suggested to them that instead of always reacting to what the Corps provides them, I said, why don't I do the modeling for you and we develop our own alternatives and provide them to the Corps and make them react to us, which I think is a great way for people to behave. And this is the way environmentalists and scientists need to do to get our way more integrated. We don't want to always be reacting. Yes.
So forgive my ignorance, but there must be an MFLs for Apalachicola. And so what role could sort of MFL-based framework be used here to anchor around sort of crucial flows at certain times of year? Or
now remember the disparity among the water management districts, where with funding that in Northwest, they don't have the funding that other places have, so they cannot do things to the extent and to the detail that other districts have, unfortunately. So they do have them, but they do have them, and the question is that do we have enough information to do that? But I think it's this avenue of metrics is how you can tie management to research to ecological needs. And I would really love to see it go forward and really be done in earnest by Florida so that when we approach the other states. And one of the things to understand is over 90% of our water in this river comes from Georgia and Alabama. So we cannot do this alone, period. Any other questions? Yes.
What is MFL?
Minimum flows and levels.
Any other questions?
Sorry, one last. So there aren't any metrics now?
There are some, but they're not adequate and they're not good enough. And we need to have them with good, strong scientific support, good logic, open, and they need to be developed by someone other than me alone. And it needs to be something that we can come forward, that the state has a position, and we can say, this is what we want, this is why we want it, and this is how it works. And one of the things, I spent 2 years being tortured by, I use a different model than this Corps of Engineers, but I went through with my work with Fish and Wildlife and calibrated my model with the course, where I come up with comparable answers. If you put the same management approach and the same level of consumption and the same local inflows, I come up with the same answers. So we have tools to do this now. And what we need to do is take the tools and use them.
Thank you so much.
Welcome back, everyone. My name is Megan Lamb, and I'm the Stewardship Coordinator here at NERR. Our first speaker this morning for this session is Kira Allen from the University of Central Florida. Kira is also a past recipient of our National Estuarine Research Reserve Margaret Davidson Fellowship. So she's just wrapped up her fellowship and it's been a pleasure to work with over the last few years. She's going to be talking about her work looking at synergistic impacts of climate change and human-induced stressors on the Apalachicola food web. Kira, it's all yours.
Yeah, so hi, I'm Kira. I was ANER's 2020 through 2022 Margaret A. Davidson Fellow. My research for the fellowship involved modeling the synergistic impacts of climate change and human-induced stressors on the Apalachicola Bay food web. And today I'll be presenting some of the final results of that project. So for a bit of background, this project focused on changes in river flow and sea level rise because freshwater reduction and sea level rise are two major climate and human-induced stressors for the Apalachicola Bay region. And as I'm sure many of you are aware, there's a decades-long Supreme Court legal battle with the Apalachicola Chattahoochee Flint River Basin over increasing upstream freshwater withdrawals by Georgia. And that case ended up being dismissed in 2021, meaning that Georgia is able to continue with those increasing freshwater withdrawals. And another stressor facing the Apalachicola Bay region is sea level rise. So this graph on the right here shows the trend in sea level since 1970, measured at the NOAA tide gauge in Apalachicola. And since then, sea level has risen by about 2.82 millimeters per year. Now, the combination of reduced freshwater inflow and sea level rise leads to an increase in salinity. With a high likelihood of increases in both of these factors going into the future, it's important to be aware of how these changes impact species in the Apalachicola Bay system, particularly when it's home to many commercially and recreationally important species. So the aim of my study was to address how will changes in river flow and sea level rise affect the Apalachicola Bay food web. A coupled hydrodynamic and food web model was used to simulate future changes in river flow and sea level rise in Apalachicola Bay from 2020 until 2050. The food web response was measured in terms of changes in species biomass over space and time. And I also conducted a survey of Apalachicola Bay stakeholders to assess local ecological knowledge on species and environmental changes in the bay. The results I'll be presenting on today for both the model and the survey will primarily focus on how changes in river flow and sea level rise impact commercially and recreationally important fishery species and the broader food web and human community of Apalachicola Bay. So the food web model for Apalachicola Bay was developed using EcoPath with EcoSym and EcoSpace food web modeling software, or EWE. The data used to construct the model primarily came from NERRS trawl monitoring surveys from 2000 to 2019. In the interest of time, I'm just going to give a pretty brief rundown of how the food web model was developed. So the baseline components of the model consist of measures of species biomass, values for production, consumption, species diets, and fishery landings. The model was calibrated over time using time series of biomass, environmental conditions such as salinity and temperature, and fishing effort. And then the species tolerances to environmental conditions are also defined, which enables the model to estimate measures of species biomass over time in response to environmental changes. And EWE is able to represent changes in environmental conditions and species biomasses over both time and space. So the final output looks something like this map on the right, where warmer colors indicate higher values and cooler colors indicate lower values. So the spatial distributions of salinity and temperature used to drive changes in the food web model were output by a hydrodynamic model for Apalachicola Bay. This model was developed by my collaborators at Tulane University using Delft 3D modeling software. It incorporates data on depth, tides, freshwater inflow, salinity, and temperature. So the hydrodynamic model was used to simulate future scenarios of river flow and sea level rise from 2020 through 2049. 4 different scenarios combining either low or high river flow and sea level rise conditions were used. These are defined in that table at the top. So the low river flow conditions were based on historically low Apalachicola river flow levels from the year 2012, and high river flow conditions were based on historically high flow levels from 1964. Sea level rise conditions were based on the observed rate of sea level rise for Apalachicola Bay. And as I mentioned earlier, sea level in Apalachicola Bay has risen by about 2.82 millimeters per year since 1970. So this rate of change was used to represent future low sea level rise conditions, and a doubled rate of change, so 5.64 millimeters per year, was used to represent high sea level rise conditions. So the 4 different river flow and sea level rise scenarios were run through the hydrodynamic model, which output measures of water temperature and salinity in response to the changes in river flow and sea level. The output from the hydrodynamic model was used as input for the food web model, which was then able to display changes in species biomasses over time and space in response to the environmental conditions. So in addition to the model simulations, I also conducted a survey of Apalachicola-based stakeholders aimed at assessing local knowledge and perceptions of which species were considered commercially or recreationally important, and then how changes in river flow and sea level rise might affect fishery species and the human community of the bay. The graph I have shown here is a breakdown of the different types of stakeholders who ended up participating in the survey. The results of both the model simulations and the stakeholder survey offer a comparison of different knowledge types to assess how changes in river flow and sea level rise affect the Apalachicola Bay food web. So the analysis of these results focused on the impacts to commercially and recreationally important fishery species and the broader food web and the human community of the bay. So before getting into those results, I first want to show how the environmental conditions changed across the feature scenarios to provide some greater context for the species results. So these outputs from the hydrodynamic model compare the annual range of water temperature and salinity between 2019 and 2049 for each of the future scenarios. And then I've also included the percent change between those years as well. And on these plots, the scenarios are labeled by the river flow conditions first, followed by the sea level rise conditions. So the name low high, for example, refers to low river flow, high sea level rise. We see with these results, there is an increase in temperature across all future scenarios, and then an increase in salinity during the low river flow scenarios and a decrease during the high river flow scenarios. So now getting into the species impacts, species of commercial and recreational importance were determined from the stakeholder survey. In the survey, participants were given a predefined list of species to rank from most to least commercially or recreationally important. And it was noted that oysters were excluded from this list because the aim of the study was to focus on other species. So these graphs show the results from the survey. And in this presentation, I'm going to focus on the top species groups for each category. So for commercially important species, this was commercial shrimp, and recreationally important species, this was flounders. So looking at the food web model results, white shrimp were chosen to represent the commercial shrimp category, and Gulf flounder were chosen to represent the flounders category. So in the model, both juvenile and adult age classes of white shrimp were represented. We see the biomass for both juvenile and adult white shrimp was predicted to increase during the low river flow scenarios and decrease during the high river flow scenarios. And then Gulf flounder biomass decreased across all scenarios. The food web model also gives a visualization of the spatial changes in species biomasses. So biomass for both juvenile and adult white shrimp was highest during the low river flow scenarios, particularly in the southwestern region of the bay. And then for Gulf flounder, for all future scenarios, flounder biomass was low across much of the bay, except for near 2 small passes connecting to the Gulf of Mexico. And something interesting to note about these results that we also saw with the environmental changes is that they look a lot more similar between scenarios of the same river flow conditions than between those of the same sea level rise conditions. And this indicates that Apalachicola river flow seems to have a stronger influence on these variables compared to sea level rise. So in the stakeholder survey, participants were asked how they thought a future reduction in river flow and increase in sea level would impact the selected populations of commercially or recreationally important fishery species in the bay. The majority of survey respondents thought a future reduction in river flow and increase in sea level would lead to a decrease in commercial shrimp abundance, as well as a decrease in flounder abundance. So comparing the survey results with those of the food web model, in the case of white shrimp, stakeholder perceptions differed from the model output. The model predicted an increase in biomass during the low river flow scenarios coupled with both low and high sea level rise, while the survey respondents anticipated a decrease in shrimp abundance. Now, changes in white shrimp biomass in the model are largely based on their environmental tolerances that were derived from the trawl monitoring data. So in the model, white shrimp tolerated a broad range of salinities and had a preference for warmer temperatures. Now, the impacts anticipated by stakeholders may be based on historical trends that have occurred in Apalachicola Bay, where shrimp landings have declined during times of drought. However, there may have been other factors that played a role in this decline, such as habitat loss, an influx of new predators, or disease. And these were factors I was not able to take into account with the food web model. So for Gulf flounder, the model results did agree with the stakeholder perceptions. Both predicted a decrease in abundance in response to reduced river flow and sea level rise. And in the model, flounder had a preference for higher salinities and higher temperatures. So with the increase in salinity during the low river flow scenarios, we might actually have expected to see an increase in Gulf flounder abundance, but that salinity increase still fell short of the optimal level for Gulf flounder, so that was why we saw the decrease in biomass instead. Looking at impacts to the broader food web, which is the next topic I want to address with this project, I examined changes in total biomass and upper trophic level diversity, which can serve as a proxy for ecosystem biodiversity. So with these results, we saw total biomass increased across all feature scenarios and trophic diversity decreased. Looking at the spatial results in 2019, total biomass was highest in the southern region of the bay, while during the future scenarios, it was highest in the northern region. And then we saw greater diversity in the southern region of the bay across all future scenarios. And the general trend of increasing biomass and decreasing diversity we see with these results, with the changing salinity regime, aligns with results that have been reported by previous studies as well. So with the stakeholder survey, it was used to assess the impacts of changes in river flow and sea level rise on the human community of Apalachicola Bay. Participants were asked how a future reduction in river flow and increase in sea level would impact the Franklin County economy, stakeholders' profession, and the stakeholders' personal interaction with Apalachicola Bay, which was defined as any engagement with the ecosystem outside of the person's profession. So the majority of survey respondents thought a reduction in river flow and increase in sea level would have a negative impact on the Franklin County economy, and then little to no impact on stakeholder profession. And most respondents expected a reduction in river flow to negatively impact their personal interaction with the bay, and that an increase in sea level would have little to no impact on personal interaction. So these results expand upon the impacts to Apalachicola Bay species populations by offering a glimpse of how changes in river flow and sea level rise might affect the human dimensions of the Apalachicola Bay system as well. So to sum everything up, I found that changes in river flow and sea level rise will have varying effects on the Apalachicola Bay food web through changes in environmental conditions, fishery species populations, the broader food web dynamics, and human community of the bay. One notable pattern was that there were greater differences between the scenarios of low and high river flow than those of different sea level rise conditions. And this implies that Apalachicola River appears to have a stronger influence on these variables than sea level rise. So with the model results, we saw that low river flow scenarios resulted in an increase in biomass for commercially important white shrimp and a decrease in biomass for recreationally important flounder. And then across all scenarios, we saw an increase in total biomass and a decrease in upper trophic level diversity. The stakeholder survey revealed some anticipated negative impacts of a reduction in river flow and sea level rise to the Franklin County economy and stakeholder personal interaction with Apalachicola Bay. And then one of the benefits of this study is that the model will remain available as an adaptable tool that can be used by ANER or other interested parties to continue to assess the impacts of climate and human-induced stressors on the Apalachicola Bay food web. All right, thank you for listening. I'm happy to answer any questions you might have.
Sure, lovely talk. What I'm curious about is how, I guess, temporally sensitive the model is to sea level rise. So the high scenario you used was 5.5 millimeters a year, but like the last decade here is actually going a little over 11 millimeters a year. So if you like double basically what your scenario is, so if you take it that high, would it respond that quickly?
Yeah, so the scenarios we used were definitely a bit conservative. I've noticed that sea level rise has actually been increasing at a much faster rate. But those were, the conditions we used were really just kind of a baseline. So it would be really interesting to look at more dynamic sea level rise scenarios and see what changes could happen as a result of that. Because definitely it seems to be increasing faster, and it's not always the same rate. So that would definitely be a future expansion on the study.
Chad, if you want to go ahead and unmute yourself, you can ask your question.
Okay, thank you. Thanks, Kara. I have a question about this white shrimp biomass dynamics. It looks like you're showing that those are increasing as the salinity was changing, and I was wondering, is that biomass projections influenced by predator-prey dynamics in the food web model? As I would suspect, as the salinity changes in the bay, that affects this white shrimp, that the species would move in the bay. More predators would be going after the white shrimp, so there might be a more food web dynamic situation going on with the white shrimp with predator-prey interactions. So I was just wondering if you looked at is your modeling sensitive to those dynamics, or if you could talk about those
Yes.
interactions with it.
Yeah, yes, so the model does take into account predator-prey dynamics, but it's not able to account for an influx of new predators that weren't very abundant in the system before. So the model has a list of about 50 species. I based it on the most abundantly caught ones in ANER's trawl surveys, but a lot of those like higher level predators and species that come in from offshore are not particularly well represented in the model. So that could definitely influence the white shrimp populations more. The way this model is set up, it was not able to take into account an increased number of those species that weren't present in previous years. But it does take into account the existing predator-prey interactions.
Okay, and we have one more question in the questions box from Nikki Dix. How intuitive is the model to use, and do staff need training to use in the future?
Sorry, what was that?
How intuitive is the model to use, and do staff need training to use it in the future?
Okay, yeah, so the model, it's all through EWE, which there's a lot of documentation on how to navigate EWE. I think it's fairly intuitive, but it definitely takes a bit of learning. And Jason he has the model now because I worked with him very closely on this project. I've walked him through how to navigate the model and look at the different results. So he's starting to get a better handle on that, and will hopefully provide some guidance to other ANER staff if needed. I'm always available to help as well, but yeah, it definitely takes a bit of learning, but it's not super difficult. So I would say it's fairly intuitive.
All right, thank you, Kira.
Thank you.
All right, up next, we have Dr. Allison Watts from the University of New Hampshire. And Dr. Watts will be discussing eDNA monitoring for fish and biodiversity in the NERRS.
So thank you so much for inviting me to this. I do really wish I could be there in person because it is snowing like stink up here in New Hampshire, and it would be much nicer to be down there. I am Allison Watts at the University of New Hampshire, and I am one of those people who is a collaborator from fairly far away. So I'm up here in New Hampshire, but I get to work with these awesome folks down in Apalachicola and NERRS all over the country. So we have collaborators all over the country working on this project. And so it's a network of people from a variety of different places. So just a little quick introduction to me. I got to go to Apalachicola a couple of weeks ago, and I was very, very happy. It was a really nice visit, and there I am, evidence that I was actually there. But I'm back in New Hampshire now, and I'm in the Department of Civil and Environmental Engineering. And the part that's interesting about that is that I'm not a biologist. So I'm going to be talking to you about DNA, and I'm going to sound like I actually know something about DNA. But my background is environmental engineering, and it's really in water resources assessment. So I've done a lot of work with water quality from a chemical point of view. And what we're doing here is we're diving into DNA as a way of a sort of additional tool in the toolbox for assessing ecosystems. So I'm going to do just a real quick overview of what eDNA is, and hopefully it will be useful. eDNA is just kind of a cute term for DNA that's removed from an environmental sample. So basically everything, not quite everything, but almost everything that's alive has DNA, and as we move around in our environment, we shed it. So it comes from hair, scales, for those of us who have scales, skin, waste products, reproduction. So when animals reproduce, when eggs are released, there's often a flush of DNA into the system. So the DNA from all of these organisms is sort of out there in the environment as this soup of information that we have not really been able to access. But as the technologies are getting better, we're able to start using that information to better understand the environment. And it's also helpful to remember that some species have shed more DNA than others. So things with hard carapaces like crabs don't shed a lot. Think about slimy things that are always dripping stuff into the environment. They do shed more. So different species shed more or less DNA. The general concept is pretty simple. You collect the samples. These are some students at UNH. They're about to drop a bucket over a bridge, and they're going to pull up a bucket full of water. We take that water and we concentrate the DNA or the particulates that are on it onto a filter. So here they are in the lab filtering. And then we take that DNA, we extract it from the filter, we amplify up the portion that we're interested in, and we do some bioinformatics to try and match the DNA that we've amplified to the species that we found in the sample. So this is not my slide, but this is sort of a common, these are the cool things about eDNA that are potentially transformative as we think about doing ecosystem monitoring. So it can be a lot cheaper than sending a lot of people out into the field. If you can just do a single sample, you need just much fewer people. And in theory, you can get those results in a much shorter period of time. So you can get results within a couple of days or weeks. Whereas when we send samples out for, say, a microscope analysis, it takes months, in some cases a year. I will say that in my lab, we're not getting that turnaround time, but we are optimistic that it can be done. There's a sensitivity and accuracy. So because we're using the DNA to do the species identification, we are able to resolve species that may look very similar in the field, or that may be very small juveniles that are hard to differentiate just by looking at them. The flip side is that organisms that are very closely related genetically are sometimes hard to tell apart. The sampling is not invasive. So for instance, if you're looking for an endangered species and you don't want to put it in a net and damage it, if you can pick up the DNA from the water, then that's less damaging or less stressful for the organisms that you're looking for. And once you have that DNA, you can do the analyses for a broad range of different species. So you can look at fish, you can look at all kinds of different things that are in there. So, and this is just a quick overview of sort of news items about DNA. So you can use DNA for biomonitoring, ocean in a cup, everything's just right there in the cup of water. Very useful for, as I said, endangered species. And this is one I found on the internet. I don't know anything about this study, but it looked really cool to me, using DNA from sand samples in Florida to look for endangered species. So there's a wide variety of ways in which this technology can be deployed. So the project that I'm going to talk about is this eDNA monitoring for fish and biodiversity in the NERRS. What we're doing with this project, if we're taking this really cool technology that we think is potentially very powerful, and we're saying, what happens when we really road test it? What happens if we try it at a variety of different sites, looking for different species, and see what information we can get out of it? Most of the eDNA studies that you'll see out there are looking at a particular question. So, are there endangered turtles on this beach? What fish are around this reef? And we're not doing that. So we're not saying what specific question can we answer. We're sort of flipping that and saying, if we have this information, how will it help us understand the baseline conditions at our site? So if you're interested in a standardized monitoring program and baseline conditions, the NERRS are absolutely the best place to go and look for that, right? So there are, I think it's 30, but the number seems to change, but I think there are 30 sites around the country. Here are the awesome folks at Apalachicola collecting nutrient samples as part of their sampling program. And so we're working with these NERRS sites and asking what happens when we just add DNA to the existing monitoring suite that they're doing. They're already doing nutrients, they're already doing sort of water quality parameters, and now we're going to start doing DNA as well. So we're working with 10 of the NERRS program. 10 sites kind of selected to be grouped on the East Coast, sort of South and Gulf, sorry, West Coast and Hawaii out here by themselves. Each site samples quarterly. They sample 5 locations, and we're going to be doing this over 2 years, so we'll have 1,000 and some samples when we're done. We are fairly early on in this process, so I'm not going to be able to give you a lot of data. Oh, and there's our star, Apalachicola, down there. So that's, of course, one of our sites. So before we started this project, or as we were starting it, one of the things we wanted to do was understand what kinds of questions do resource managers think DNA might be able to help us with. So one of our goals is really to be able to make this information accessible and useful. So we went out and we asked people, if we can do this eDNA sampling in your estuary, what kinds? Yeah. Is that me? Okay, I'm gonna keep going.
Hey, Allison, can you hear me?
Yeah.
We're having some network troubles. Could you go back just about a couple slides, maybe 30 seconds? And I'm going to turn off your incoming video so that we might have a better audio.
Okay. About there?
All right, take it away.
Okay, 10 estuaries.
Yeah, that seems great.
5 locations. Is that better? Yeah, I will say it's very stormy here. I'm not entirely sure what the electrical situation is. So there's Apalachicola, resource managers' questions, questions that they hope that we will be able to answer with eDNA, or questions they have about eDNA. How many species can we detect? How much does it cost? And how does it compare to traditional work? So in our project at each of these 10 sites, the staff collect the samples. So here are these wonderful people at Apalachicola again. So now they're collecting the eDNA samples, and one of the things you'll notice is that they're trying to work in a cleaner environment, so they've all got gloves on, so we don't get people in all of our samples. 3-liter samples are collected, then taken back and filtered. Those filters are then sent to UNH. We cut them in half, so we have one reserved in case we need it later. We have a robotic extraction system, so we extract it, pull the DNA off. And then just I'm going to go over really briefly some of our initial results. So this is from our first 2 quarters of sampling in May and August. We had nearly 300 samples, about 181 fish species. But here's the interesting things. There's a lot of variety. So some samples we get no fish. We got 1 sample with 43 fish. That was probably Hawaii. We also get humans, dogs, dolphins, random other stuff. Eventually, we will run other primers that may be targeting some of these other types of species. So here's Apalachicola in May, sampling at 5 sites. And in that sampling, we detected 33 fish species. And you can see that here at Dry Bar, we had 21 fish species, so that's pretty good. 19, 10, 7. And then over here in Pilot's Cove, none. And we see that in the next set of samples, and we've seen that before. There are sites where, because the water is very turbid and there's a lot of other stuff interacting with the DNA, where we have a really hard time detecting the fish species in that sample. It doesn't mean the fish aren't there. It means that this method is not working really well under those conditions. And just to go into that a little bit more, this is from an earlier project in 2018. This is Great Bay, New Hampshire. These are the number of samples collected, and we've collected a lot of samples in different locations over the course of probably 9 months. There are about 50 fish species that we expect to find in Great Bay based on historical data. And you can see that over time, we do a pretty good job. We get most of the species. If we kept sampling through different seasons, we would probably be able to detect all of the fish there. So yay, that looks great. We come to Apalachicola, you have a lot more fish. So it's a much more diverse system. We didn't take as many samples, but even if we'd taken a lot more samples, we're not going to get all the fish in that system because we are just not detecting as many fish per sample, and we're missing some of the species probably due to these water quality issues. So one of the things that we're really trying to work on in this project is better ways of processing these samples. So better sample cleanup, using different primers, and really trying to figure out if we can move this curve so we're at least a little bit closer to the number of species that we expect to find there. So there's some challenges. There's a lot of people who are very excited about DNA, but there are things that you really can't do with it. So the sampling can be pretty time consuming. Sam spends hours after she spent all day on a boat. She spends hours in the lab filtering. The methods are changing really fast. So if you talk to someone and they tell you these are the methods we use, this is what you do, you go back next year, they're going to be different. So it's kind of hard to keep up with that. And the results are sometimes confusing and hard to understand. And one of the things we're really trying to work on in this project is how can we convey these results in a way that's useful and that's usable without requiring the users to learn all this stuff about DNA and bioinformatics, and that can be a little bit challenging. By the time the project is done, which will be sort of late 2024, a couple things we hope to have. Recommendations on how different types of stakeholders, different types of managers could incorporate eDNA data into their work to help them improve the management in their systems. We're working on protocols. We have methods and protocols that we make publicly available on our website, and we will try and transfer those in a way that people can use them, again, without having to have a lot of expertise. And in the end, one of the things we're really going to ask is this useful in a long-term national monitoring program? Is this type of information and the cost that's required to collect this data, is that something that is worth it? Is it worth putting it in and starting to add it to our standardized monitoring programs? And sometime in the end, as we get later in this project, we're going to be coming back to you guys in this type of forum and asking you, this is the kind of information we can get. How is it useful to you? How would it be helpful in the way you do your work in this system? Okay, I think that is what I have. It's a very fast overview. We do have a website here, and as we get more data, we will be putting it up on the website. All right.
All right, we have time for a couple of questions. Dr. Ames?
First of all, Allison, great talk, thanks. I was struck by the number of samples needed to detect all of the species, and it started me thinking about temporal variability. By that I mean, it seems like there would be certain cell types that would be more persistent than others, like a scale might persist longer than a secretion. I'm not a biologist either, so I don't know if that's true, but let's say it is. What do we know about how eDNA signals are related to just the persistence of the source of that eDNA in the first place? I mean, might you just detect the cells that are more persistent in the environment, and then you don't detect the ones that are less persistent? Maybe therefore you miss sort of ephemeral users of the estuaries. If that makes any sense at all?
Yeah, so it does, and yes, definitely, that's definitely true. So for instance, larger pieces break down more slowly. So when you're talking about something that is being shed as a very small fragment, it's probably going to degrade more quickly. We also know that warm systems, the biology just breaks down a lot quicker. So DNA breaks down a lot quicker, and I think that's one of our issues in your system is it's just warmer. In Great Bay, they're kind of frozen in place. So size, freshness, probably type of material. So how fast, as you said, scales don't break down as quickly. I think all of those things play into it. I don't know exactly which, where, why, when, but yeah, I think they're all factors.
Right. Did you detect oysters in any of them?
We don't, but the primer we're using wouldn't. We can go back in and look for that. It is, people do that. That's doable. It's just not what we have done yet.
All right, well, thank you, Allison.
All right.
Up next, we have Annais Bonilla-Johnson from Florida State University. She'll be talking about effects of embryonic maternal investment of life history and survival in 2 matrotrophic Elasmobranch species.
Hi, my name is Annais Bonilla-Johnson. I'm from FSU. I am Dr. Dean Grubbs, one of his students. So today I'm going to be talking to you guys today about how maternal investment in elasmobranchs might be affecting survival of them in the wild. So just a little bit of background. So what is elasmobranchs? They are a subclass that includes sharks, skates, rays, and sawfish. I'm not going to go into life history because it seems like it's a pretty good, we all have a good grasp of what life history is. But you can see from this picture that we have a really diverse selection of sharks, skates, and rays and sawfish that exist. Inclusive of this diversity is also the modes of reproduction that they participate in. So we have oviparity, ovoviparity, and biviparity. And all I'm really going to talk about today for this slide is just that there are live births and then there are egg cases. And then just you can see from that right-hand side that, let me see how I figure this out. Is this it? Yeah, from this right-hand side, there's just within egg cases in general, there is a huge amount of diversity. So the main thing that I'm going to talk about today is embryonic nourishment. And there are 2 modes of embryonic nourishment, one being leucotrophy and the next being matrotrophy. So here we have an embryo and it's attached to a yolk sac. And so I'm kind of going to describe how embryonic development usually happens in elasmobranchs. So we start off with the yolk sac, and then we slowly have our embryo that uses that yolk sac as nourishment in order to develop. So once we get over here, you see that our embryo or our embryo is a little bit larger than our yolk sac, so it's consuming it in order to develop. Once we have a full, complete consumption of this yolk sac, that's when we get into the difference. I might have hit pause. Okay, the difference between leucotrophy and matrotrophy. So leucotrophy describes species that solely rely on that yolk sac during embryonic development. Matrotrophy is once that yolk sac is depleted, the mothers will invest some kind of other nutrition to their embryos to get them to full term. So we see here is an example of what myliobatiforms participate in, so rays, which is lipid histotrophy. It could also be mucin histotrophy, but I'm going to be focused on lipid histotrophy. The other forms can be oophagy, which here we have a porbeagle embryo. And so they essentially absorb other ova or eggs to get the rest of the nutrition that they need to get to full term. One we're way more familiar with is placental connection. So bonnet heads do placental connections. And then one picture that I don't have on here, which some people know of, is intrauterine cannibalism, so autopophagy. So those are the different kinds of matrotrophy that can be established in some of the elasmobranch species. So focusing on lipid histotrophy and rays, we see this uterus here. So once this yolk sac is depleted, we have the uterus will start to secrete what is called histotroph. And we're unsure, it's not very thoroughly analyzed in ray species or some elasmobranch species that also participate in histotrophy, how often they secrete as well as the content that's within it. So we have the secretion here that happens within the uterus from their villi, and this is what it can look like, the different colors from throughout the different gestational periods. And this, the extra content will get them to full-term embryo here, ready to pup. So these are the two focus species for my project. So what I'm going to be talking about today is all proposed work from my dissertation. It's a lot to fit in, so I'm going to try to pack it in as much as I can. But Hypanis sabina, this is Atlantic stingray, as well as Rhinopanera bonaesis, which is the cownose ray. They both are viviparous, so they both have live births, as well as participate in lipid histotrophy, which is the reason why these two were selected. They're found out in Apalachicola Bay. And the difference between these are that they have two very different life history strategies. So our Atlantic stingray has 1 to 4 pups per litter and has a 4 to 4.5 gestation period. And our cownose has 1 pup about every year and a year-long gestation period. So we have a difference in maternal investment that we're seeing. So in order to collect these specimens, they will be collected every month. 10 specimens of each species will be collected every month, and it'll be in collaboration with the THIM sampling program through FWRI, using scenes, trawls, and then gill nets. So to address the first aim, we want to try to see how this maternal investment might be affecting survival, so might be affecting their physical performance, and differentiating species that might have larger amounts of maternal investment to see if they might be more at risk because of this large amounts of maternal investment. So my first aim has to answer this question that we don't know, is how often are they secreting this histotroph, and what effect does this histotroph have on the level of maternal investment? So that looks kind of winky. In order to do this, they'll be collected, like I said, monthly in order to try to get specimen at all gestational periods. It's unclear on when they're secreting this histotroph, so it's based on when we're collecting them and whether or not we see, whenever we're dissecting, whether or not they've secreted this liquid. I showed this a little bit beforehand, but this was done in the red stingray, and this just kind of shows the difference from the periods of gestation of what just the color in general can look like. So aside from the physical description will be recorded, so will the volume and the frequency, and then samples from this will have a full biochemical analysis run on them. That includes carbohydrates, fatty acids, total energy content, to analyze chemical oxygen demand will also be run. This is just this was done in the red stingray. It's the first full, thorough biochemical analysis of histotroph for them was ran, except it was only like 1 or 2 periods throughout their gestation and not the entirety of their gestation. This is just an example of what it could look like. They analyzed protein, lipids, and fatty acids. And so here's one of the potential things that I would like to do is be able to take the content that I'm getting with the Atlantic stingray and the cownose and be able to compare it with these other published analysis that they've done. So compare it to the red stingray, as well as the only other one that's had some kind of analysis is our tiger shark. And tiger sharks are really unique in the fact that they have, although they are within the family of Carcharodontidae, which a majority of those have placental connection, tiger sharks have been shown, I think it was Castro 2016, they have this, each individual tiger shark is surrounded by a sac. And within that sac is like a clear fluid. And so Castro went ahead, oh, I don't think I have, yeah, right here. Castro went ahead and did the chemical oxygen demand values of the content within these sacs to see what the content was, as well as they looked at it over early and late stage gestation, and they were trying to see if there was a change in the chemical oxygen demand as gestation progressed. So the potential with this is being able to compare it, but also the fact that tiger sharks still have these large embryos at birth, and then they can have a litter size of up to 55 pups per litter. Placental connection is usually attributed to this large pups and these large litter sizes was what was thought. So there's potential for the content of what is surrounding these embryos to be getting them up to these big pup sizes and contributing to these life history characteristics that we're seeing. So essentially, we would just be looking at the change in the frequency or how often it's occurring, the volume, if that's changing on how much is being secreted throughout the gestation in both species, as well as if the content is changing and if it differentiates as gestation progresses. So this leads me to my second aim, which is looking at quantifying maternal investment after that. So in order to quantify maternal investment in the past, we do what's called percent dry weight change. And so with that, we're going to be using the same samples as in the previous aim, essentially taking fertilized ova here. You take your fertilized ova and then developing embryo all throughout the gestational periods that they're collected, and you dry the samples to remove the water weight. You incinerate to remove the organic weight, and with this equation here, we get the organic weight, and then we're able to track the organic weight here and plot it, and we're able to see how this quantifies levels of maternal investment, not only as gestation, the entirety of gestation, but as gestation progresses. So we'd be able to quantify maternal investment at each gestational stage, as well as be able to compare it between species. So here is just an example of what the different gestational stages might be categorized as. In previous research, they just did the embryo total length. And this negative symbol here just shows that they were lecithotrophic. So there was no amount of maternal investment in dogfish. So this leads me to my last aim, which is once the maternal investment has been quantified at each gestational stage, we then can see if there are certain gestational periods with large amounts of maternal investment, or in general, large amounts of maternal investment that might be having an effect on the physical performance of these stingrays and in turn possibly other elasmobranch species. So this would be a respirometry trial. These individuals, they would only be with Atlantic stingrays due to their size. And they would be collected in the beginning of March. They would be confirmed pregnancy through ultrasonography and then also blood hormone analysis. They would be put into a respirometry chamber. They would have a stabilization period, as well as time to make sure that their metabolism isn't affecting these trials right after eating. They'd be put into a respirometry chamber, and then essentially the oxygen consumption rate would be calculated over a 6-hour trial period. The averages of all these individuals would be taken, and then this would occur every 3 weeks for 6 months in order to get an idea of how the oxygen consumption rate is changing at each gestational period, and to see how their metabolism might be changing as this gestation progresses. So oxygen consumption would then be converted, oxygen consumption would then be converted to metabolic rate, and that would be used to assess the physical performance. So that would allow us not only to quantify how gestation in general affects a species as gestation progresses and compare them, but also be able to identify stages or specific gestational stages that might be having or making the species more vulnerable. So in turn, the significance of this is not only addressing the fact that there's this huge knowledge gap, regardless of the fact that elasmobranch reproductive physiology has been studied for the past 100 years. There's still this massive gap of how individual species as well as general species and reproductive modes how they contribute to a species' survival in the wild, as well as just their reproductive patterns. In addition to that, that will allow us to adjust some of the fishing regulations, temporal location, in order to kind of morph it to be able to protect some of our more vulnerable species of Elasmobranch that might be more vulnerable at certain gestational periods, or in general, if we find that higher amounts of maternal investment have an effect on their survival, we'd be able to pull those out and protect them better. And that's it. You guys have any questions? Oh. That's my shark. Yes?
So you said you've been monitoring the stimulus for 6 months?
Yes.
And so I noticed that's longer than their gestation period?
Yes.
So are you going to compare like what their metabolism is like post-birth as well?
Yeah. So one of the things with that is also potentially being able to understand the metabolism, how it changes right after parturition too, to be able to see exactly how much energy they're consuming as well, right after parturition, or maybe even during, right before and after. That's what I'm hoping we also get. But also the before period, but right when they're pregnant and then after, to be able to get that right after parturition, and then enough time for them to be able to stabilize and have a comparison from when they're initially pregnant as well.
Thank you very much.
Up next, we have Ashley Dawdy from Florida State University also. Ashley will be talking about movement behavior and habitat use of Cownose rays in Apalachicola Bay.
Thank you everyone for being here. I'm a PhD student at Florida State University. I'm studying under Dean Grubbs at the FSU Coastal and Marine Lab. And today I'll be talking to you about an ongoing part of my dissertation, looking at the movement behavior of Cownose rays in Apalachicola Bay using acoustic telemetry. All right, so understanding the habitat use behaviors of mesopredators is very important in constructing appropriate species management. And we have seen issues regarding this phenomenon with several species of rays in different geographic locations. And so one example that we saw of this is the California bat ray. In California, a fishery was started for this species because it was thought that they were predating on commercial oysters. However, in the end, this did not help the oyster population at all, because it turns out bat rays were actually primarily foraging on a crab species that eats oysters. Another situation that we have seen in the recent past is that of Cownose rays in the Chesapeake Bay, due to a purported marine trophic cascade that was presented that incorrectly suggested that Cownose rays were the cause of commercial bivalve population decline. A directed fishery was established for Cownose rays, which included all kinds of crazy large-scale derbies that happened specifically during mating season when Cownose rays were aggregating to mate and pup. And it was later found out that Cownose rays were not actually the cause of that. So all of that was pretty much for nothing. So a little bit about how this project in the Bay came to be. So just to give you some context, a couple of my former lab mates ran some fishery independent shark surveys in Apalachicola Bay between 2018 and 2021. And you can ignore all the symbols on this map for now, but just focus on the fact that it's split between the west side of the bay in blue and St. George Sound to the east, which is in yellow. Something we noticed during these surveys was that we were sporadically capturing young of year Cownose rays that had likely been pupped just days to weeks prior than when we were capturing them. As far as Cownose ray life history goes, they have a very conservative life history, which makes them potentially vulnerable to population decline. Cownose rays currently are listed as near threatened on the IUCN. However, they have never had any official type of stock assessment done before. They mature at a late age, which is between 6 and 8 years in the Gulf of Mexico. Mature females produce 1 pup per year. They have nearly a 12-month gestation, and they do not take a year off in between mating. So mature females are pretty much constantly pregnant, and building up pups. Due to all of these factors combined, the maximum population increase rate for cownose rays is estimated to be about 2.5% per year, which is quite low. Okay, so moving on to their distribution and movement behavior. Cownose rays are present in a lot of locations, which you can see on this figure over to the right, showing their geographic range in blue. And we know that cownose rays are highly migratory along the east coast of the United States, where they undergo long annual migrations between South Florida in the winter and Chesapeake Bay in the summer, where they reproduce. However, we are lacking movement data for individuals in the Gulf of Mexico. We know through several diet studies that cownose rays are durophagous mesopredators, meaning that they primarily prey on shelled invertebrates. They're considered to be opportunistic and rather generalist feeders. If you look at diet studies between different areas, they're totally different. But diet can include taxa such as crustaceans, polychaetes, crustaceans, bivalves, as well as other invertebrates.
I think we got it sorted out.
Cool. And then cownose rays are predated upon by larger Elasmobranch. So in this middle photo, you can see pretty much an entire cownose ray, jaws and all, that I found in the stomach of a great hammerhead. So there are several concerns for conservation with cownose rays, as you may have gathered already. In part being that there have been years and years of targeted culling events for this species, but we've never assessed the population, so we really have no way to know how that affected the population. Recently, the presence of a morphologically indistinguishable cownose ray of a different species was confirmed to have an overlapping geographic range. So the Brazilian cownose ray, it turns out, is not only in Brazil, it's also in the Gulf and in the Atlantic. So that introduces challenges to studying those species, as well as the knowledge gaps that I mentioned regarding their behavior in the Gulf. So this project has a couple of objectives, but it isn't in its early stages. And so today I'll just be talking about my first objective, which is pretty broad. I would just like to define habitat use patterns of cownose rays across various life stages in the bay. So I'm interested in finding out how long or what proportion of the year cownose rays are actually in the system interacting with other species, and what habitats they are primarily using when they are in the system, as well as how that changes over ontogeny. In the future, I would like to also assess trophic interactions of cownose rays with other species, but I'll get into that a little bit later. I chose my fishing location a bit randomly based on the limited catch data that we had for cownose in our Apalachicola Bay surveys, as well as data shared with me from Dave Gandy at FWC about where they have caught some cownose and their fishery independent monitoring, sampling. However, that was all very sporadic. So I decided to fish in East Bay because it looked like there might have been something going on there. So the first day that we went out to fish in East Bay, we actually found a mating event happening, which was very cool. Tons of males and females chasing each other around at the surface. We put out one gill net that we started hauling after, what, like 10 minutes? And there were 70 adults in that gill net, all the females being super pregnant, as you can see in this photo, about to pup any day, or looked postpartum as if they had just pupped very recently. Something to note was that the salinity was between 3 and 6 in both years of me sampling here and seeing pups getting dropped. And so that's pretty interesting in itself, because that's a very low salinity for an elasmobranch to be dropping pups in. That is not a bull shark. And so this is just to summarize the sampling effort in East Bay. So we did fish in 2021 and 2022. You'll notice that it took me a lot longer in 2021 to get all the samples of the right life stage I needed, so we caught more overall. In May, we only fished for a couple of days in 2022 and still captured 58 rays. And so of the individuals that were caught, a sample of those were tagged with Innovacy V13 passive acoustic transmitters. And so that is just a quick surgery that's done to implant the tag internally. Those tags are pinging at a fixed rate. And so if they ping within range of a receiver, they will be picked up. Other individuals were sampled for any combination of fin clip to be used for genetics, muscle sample for stable isotopes, and gut contents. So this figure is just showing our acoustic array in Apalachicola Bay. So each triangle is representing a receiver, and they either have this fixed rig where they're sitting on the seafloor, or they're augured into the seafloor in this buoy in areas that are susceptible to trawling to attempt to reduce how many receivers we lose during the study. To summarize tagging effort, between the 2 years of sampling, I tagged a total of 36 individuals. This includes 12 of each group, so 12 mature females, 12 mature males, and 12 young of year individuals. We do not catch enough juveniles to tag juveniles that are greater than a year old but not yet mature. And so my data, this is very preliminary. It's just going to be showing you data from individuals tagged in this first year. So just the first 20 individuals, which includes about 17,000 detections and at least an 80% survival rate, which is pretty good, in my opinion. Okay, so these figures are just showing you some broad patterns that we are seeing with our data so far. And so this figure is just showing you throughout time about the first year of tracking, how many individuals are actually being detected within the system at a given time. And so you can see that in October, this begins to drop off. We see individuals leaving the system. However, there are a few that were detected every month of the year, which indicates that there are at least some individuals that are staying pretty close to the system. So either using the system or not going super far, perhaps going slightly offshore when needed for thermal refuge and then coming back in. These figures are just showing you, starting from left to right, the number of detections in total for each individual. So these two that have almost none are the two that probably died. The middle figure is showing how many days once they were tagged it took for them to be detected within the acoustic array. So you can see that most were detected pretty much right away because we do have a receiver up in East Bay. And this last graph is showing you how many days of the year they were detected in the system. And so you'll notice we do have some individuals that were detected over 300 days within Apalachicola Bay. These last few figures are showing you movement between the east and west side. So if you think back to that blue and yellow part of the map with the bay side to the west and the St. George Sound area to the east, this is just showing us through time how individuals might be going back and forth between those two areas of the system. So this is just showing for young of years, which overall is pretty boring compared to the others. You can see these tick marks going along the, this orange line, which is just showing you that those individuals are still being detected on the west side of the bay. These dots are showing you wherever they were when they were last heard from. So you can see that most were last heard from on the west side of the bay, but there was one that might have gone off the east side. And very little movement between. So most of the young of years are staying over in that west side of the bay shortly after being pupped. Switching over to looking at mature males, we see overall a pretty similar trend. So males are staying in the system or staying on the west side of the system until about October or November. From there, they may move back and forth or they may leave, with exception of that one that stayed throughout the winter. So now when we go to looking at mature females, we see that this is very different, which is very interesting. So we can see that throughout the summer, females are making lots of movements between the east and west side of the bay. and they appear to be doing this in somewhat a coordinated fashion. So we are seeing them get detected within the same periods of time over on the east side. And when you actually look at the acoustic data itself, you would see, if I mapped it out, that all of these detections are all happening at the same receiver. And so something is going on the east side of the bay that is causing mature females to go over there frequently. So something on my agenda this summer is to look at what is over there on scuba. And this last figure, sorry, the color seems to have disappeared from it. This figure is showing you the average time that, just for mature females, that they're arriving in a new half of the system. So on average, what time are they first getting picked up on the east side of the bay and then back on the west side? So we can see that for, my color coding is gone too, but if it was there, you would see that on average, they're arriving at the east side of the bay or the Marsh Island site right around dusk, and they're returning to the west side of the bay pretty much in the middle of the day. And so my thoughts are that potentially they could be going over to the east side of the bay to potentially a foraging area, and then returning to the west side of the bay during the day when large Elasmobranch predators are likely to be less active, reducing their predation risk on their return back over. So this red circle is showing you where that acoustic receiver is that the adult females are getting detected at. It's an area called Marsh Island. I haven't gotten in the water there in a while, but I think I remember lots of polychaetes being there. So I'm interested in doing some surveys on scuba to see potentially if there's any rich prey foraging areas over there. So again, this is in its very early stages. I'm continuing to add data from that second round of individuals that I tagged. So hopefully this gets a lot more interesting soon. And then I plan on potentially adding a gut content and stable isotope analysis component to look at what Cownose rays might be eating in the system. And I personally am interested in seeing if their movement behavior or proportion of time spent in different habitats correlates with what is seen in their gut contents. And then in the end, depending on how much data I get, I'd like to look at space use estimates across life stage as well. So that is all I have. My slide will go. I would like to thank all of my current and former lab mates who have helped this project happen, as well as all the staff at the FSU Coastal and Marine Lab, and all of the volunteers and graduate students and divers that have helped me out in the field to make this all happen. So thank you. I'll take questions if there's time.
Are you going to be increasing your tagging effort? Are you doing more tags? Or are you done tagging?
That's a good question. So originally I was not planning on putting any more out, but it's kind of going to depend on how much data I end up getting. So we're about to do another round of downloads that will hopefully have data from that whole second batch. And so if it looks from that like I didn't get enough, then I'll probably be looking for more money to do another round.
So I was going to say, because we do get them occasionally,
Okay.
and we do get them from the side.
Mm-hmm.
It's not every time you go out.
Yeah.
But if you want to throw some tags or if you want to come out.
Yeah. Okay. Thank you.
I was going to say, with movement towards the east, I would expect all that seagrass habitat to just be awesome.
Yeah. Yeah. Yes.
Brandon, why do they move up the coast?
Is
there overlap? Like, are they sharing certain habitats with the
on the East Coast? Yeah. So on the East Coast, they are, they're moving in the winter, they're moving south for a thermal refuge because it gets too cold. And in the summer, they're moving up to the bay to pup, likely because that's a very productive area. And if they're able to survive for long periods of time in this really low salinity water like bull sharks can. They could potentially be doing a similar anti-predator strategy of dropping pups in an area that less predators have access to. Yeah, but they do overlap. So there's a paper where a bunch of genetic sequencing happened, and Brazilian Cownose rays were confirmed like right outside of Indian Pass, not inside of the system, but outside, directly outside. I will say I sent off like 80 fin clips after the first year of sampling, and not a single one came back as Braziliensis, which was surprising to me. But yeah, on the East Coast, people that have tagged Cownose have accidentally tagged a bunch of Brazilians and found out later. So.
No questions from the online audience, but one comment from Dr. Watts who says they can differentiate between Brazilian Cownose in the eDNA sequence.
That is cool. Yes, it's like a very small mitochondrial marker that we use. So awesome. Thank you.
Welcome back, everybody. My name is Ethan Bork. I'm part of the research team, and it is my great pleasure to introduce to everyone Dr. Raymond NERRS from Penn State University as he talks to us about the carbonate system in Apalachicola Bay.
Hey, thanks everybody. I'm sorry I can't be down there. Always enjoy my trips down to the reserve. Hope to be getting back down in May, or at least Penn State contingent will be there. So I'm gonna talk to you today. This is not exactly our project in Apalachicola Bay, but I got interested in the work that Jason and Ethan started, and we had done similar work on the carbonate system in Chesapeake Bay, and so this project sort of fell in our laps, and we've been working together, me and Jason Garwood, Ethan Bork, and research scientist in my group, Maria Herman, who's actually done really all the heavy lifting. All the graphs that you'll see in this presentation were made by her. So let's see. All right, so the slides are a little screwy. Sorry about that. I really thought I had prevented it by sending a PDF, but I guess that doesn't work. So my first slide here is just a description, very simple description of what the carbonate system is. And, you know, it's simply the equilibria of CO2 and its dissociation products. So you're kind of seeing part of that here in kind of a messed up way, but carbon dioxide reacts with water and there's an equilibrium. This should be an equilibrium sign here. You can see my cursor. Just want to be sure about that. Are you able to see my cursor?
Yes, we can see your cursor.
Okay,
no problem.
Great. Thanks so much. Okay, so right, CO2 reacts with water and this dissociates into hydrogen ion and bicarbonate ion here, shown here. And these are very, very rapid reactions, order seconds. So there's an equilibrium that's established here, and it's a function of temperature, salinity, and pressure if you're deeper in the ocean. And then there's further dissociation step here where the bicarbonate ion splits up into another hydrogen ion. So there should be two hydrogen ions here. And the, let's see, webcam, my webcam was closed. Everything okay? You still with me? Something changed on my end. You're no longer seeing me?
I disabled your webcam.
What's
I
that?
disabled your webcam temporarily.
Okay.
We're having a very difficult time hearing you, so we disabled your webcam to increase the ability to stream the audio.
Okay, that's great. Yeah, I'm not the most photogenic anyway, as it turns out, so no loss there. Okay, so anyway, there's a second dissociation step into carbonate ion and another hydrogen ion. Again, it happens very quickly, And so there's equilibria among these sort of three main carbon species. And you can see that the hydrogen ion is also involved. And so why is it important? Well, carbonate system influences many important processes. For example, the calcification of marine organisms depends in large part on the carbonate ion concentration. And there's other processes that depend directly on the amount of CO2 that's available. For example, seagrass growth is influenced by the amount of, it's sort of CO2 limited. So, you know, there's numerous biological processes that are affected by the carbonate system. And the carbonate system also influences the exchange of carbon dioxide with the atmosphere, and estuaries play a role in the global cycling of carbon. They're a small but not trivial source of carbon dioxide to the atmosphere. So they affect the large scale, you know, global carbon budget, and regionally they're very important in carbon budgets. And then carbonate system measurements are kind of used as tracers, and they can be used to quantify ecosystem scale, biological rates, like really important things like community photosynthesis, respiration, calcification, calcium carbonate dissolution. So these are some of the reasons why the carbonate system is important, and we might want to study it. All right, so what measurements are needed to quantify the carbonate system? Well, I showed you the two main dissociation reactions. There's also an equilibrium reaction that involves the dissociation of water. And then seawater must also be electrically neutral. So these are 4 quantitative constraints on the carbonate system. But turns out there's 6 unknowns. I introduced you to 4 of them already. These 3 inorganic carbon forms, the hydrogen ion, the dissociation of water also will involve the hydroxide ion. And then there's the total alkalinity, which is the acid neutralizing capacity of water. It's usually measured by a titration. And the main things that get titrated out that buffer seawater are bicarbonate ion and the carbonate ion. This is an approximation. This is called the carbonate alkalinity here. The total alkalinity is really what's measured, and needs to be measured in order to constrain the system. So that means you have 4 equations, 6 unknowns. That means you got to measure 2 things. So the 2 things that are usually measured are the pH, basically the hydrogen ion concentration, and they've been measuring this at the reserve for really decades. The total alkalinity is another common measurement. The partial pressure of carbon dioxide is another thing that's measured, given its role in the gas exchange and carbon cycle. And then all of the inorganic forms together, which is called the dissolved inorganic carbon. So the ones that are really kind of important and interesting are the alkalinity, because it's a conservative quantity with respect to temperature and salinity change. It's unlike the pH, which is kind of honestly a nightmare variable, because it varies for like many different reasons, and it's sort of hard to make sense of. Total alkalinity has this conservative property. Dissolved inorganic carbon also has this conservative property. So if it changes, then you can attribute it to very specific processes. What I'm going to be presenting today are pH and total alkalinity measurements. Before we get to that, let me just say, what do we already know about the carbonate system in Apalachicola Bay? Well, there's 3 main studies, at least that I'm aware of in my literature review. There's a study in the late 90s by Chanton and Lewis, where they measured DIC and isotopes of it. And what they found is that the variability was really dominated by mixing, and it appeared to be almost conservative. A low DIC from rivers basically mixes with high DIC from seawater. this, as I said, they've been measuring pH down at the reserve for really decades. And there's a very nice paper by Bowman and Smith that analyzes those data, but actually data from 15 other reserves. So it's a really, really beautiful cross system synthesis of pH and oxygen. And what they found at Apalachicola and at other reserves, that the pH variability they documented pH variability and then described its relationships with, they could explain a lot of that variability with oxygen, temperature, and salinity. Then a little bit more recently, there was a very nice study by Joshi et al. Where they went out and made measurements of PCO2 and pH, and then they connected that with remote sensing and also connected it to the historical pH measurements at the reserve, and sort of made maps of the partial pressure of CO2 and then calculated the exchange of CO2 with the atmosphere. So there's been some work done, but it's sort of piecemeal. And so there was an opportunity to get a more comprehensive look at the carbonate system in Chesapeake Bay. And that's why they started in 2021. Jason and Ethan and others started to measure. They've been measuring one carbonate system variable pH, and they added a second one, which was the alkalinity, to their monthly sampling. And they're doing it at 10 sites that are shown here. Started in April 2021. I believe it's still ongoing, but I'm going to be presenting data up until October 2022. So it's not quite 2 years. And what you can do, as I said, you completely constrain the system if you can measure two quantities. So if you measure now you have the pH and the alkalinity, you can compute all these other things. So what we computed was the partial pressure of CO2 and the dissolved inorganic carbon. We computed the air-water CO2 flux from the wind speed, and this should be delta PCO2. This is another screw up in the fonts here, but that should be a delta. That's the air-sea PCO2 difference. So with that difference, we know the PCO2 of the atmosphere very well. And if you know the wind speed, you can make a pretty good estimate of the air-water CO2 flux. So we did that, and we sort of examined the spatial and temporal variability in the total alkalinity and these other computed quantities. Okay, just to provide the hydrological context for this study period, relatively high flows during this period. The mean for this 19-month period, was about 10-15% higher than the average stream flow. So relatively wet conditions. But not super unusual. Okay, so here's just, I'll start showing some of the results. These are the input variables. So the pH and the total alkalinity. And you'll see this for many quantities measured in the bay, that there's large gradient from the low salinity portion of the bay, East Bay, and the river, Apalachicola River, out towards more saline waters that are more representative of the Gulf. So there's an increase from about 7.5 in the river to about 8 out closer to the Gulf for pH. Alkalinity increases by roughly a factor of 2. The riverine alkalinity is maybe 1,000 millimoles per meter cubed. The ocean is about 2,000, and you see that that very substantial gradient there. Okay, so this is what we often do, what chemical oceanographers often do when they study estuaries, is that they plot things versus salinity. And if things plot along a line, then that tells you that you're very close to conservative behavior. In other words, you're just mixing river water here with ocean water here. So if it's a straight line, then that's telling you the behavior is pretty conservative. There's no sources, internal sources and sinks, in this case, of of alkalinity. If the alkalinity were above this line, then that would indicate that there's something producing alkalinity. If it's alkalinity below the line, there's indicating something that is consuming alkalinity. So what's tricky about this, though, is that when you look at the river water, it's varying quite a bit. So it's hard to know exactly what you're mixing with, what time period you're mixing with. So it's a little bit tricky just looking at this diagram to figure out if the behavior is conservative or not. But it's certainly, to first order, you might say that it is, and that's consistent with what Chanton and Lewis found for DIC. So just investigating what's happening at the river, we plotted it versus stream flow, and you can see that the alkalinity is, as stream flow increases, the alkalinity goes down. And this is a pretty common feature. And this really just reflects the relative contributions of base flow and surface flow in the river. Base flow dominates at low stream flows. You're getting a lot more groundwater that tends to be high in alkalinity because of weathering, basically, which will increase calcium and carbonate ion and things like that, which indicate high alkalinity. So that's showing some of that variability there. So what we did to more robustly characterize whether there's a source or sink of alkalinity is we calculate this quantity called the apparent alkalinity utilization. It's the deficit with respect to instantaneous mixing. So that's an assumption, certainly, that mixing is occurring instantaneously. But this AAU is the alkalinity you expect from instantaneous mixing minus what you actually measure in the water. And what you get from instantaneous mixing is just a weighted average given by the salinity of river water here, alkalinity river water, and alkalinity at the high salinity end member, which in this case is really Gulf water. And when we do that, we see that the AAU is generally positive, which means there's an alkalinity sink. Okay, so there's some indication, particularly at low salinity conditions, that there's some kind of sink of alkalinity. That could be something like, most likely cause would be calcification, which would remove calcium ion from water, and that would drop the alkalinity. Here's a map of the PCO2 that we calculated. This also shows that strong variability, in this case, very high PCO2 at the river end member, contrasted with low CO2 at the high salinity end member, and close to equilibrium with the atmosphere, which is around 450, 415 or so parts per million, or microatmospheres actually in this case. We calculated the flux, and before I get to that, this shows some of the temporal variability in the partial pressure of carbon dioxide. And what we see is that it's like inversely related to the oxygen supersaturation. So this is the departure on the right here, and in red is the departure of oxygen from saturation. And so you can see it's varying quite a bit, and PCO2 is varying in an inverse way to it. So it suggests really that it's metabolic control, biological control, organic matter cycling control on the partial pressure of CO2, because that's what's influencing the oxygen. So I must be running out of time. Let me wrap it up here. Here's our air water flux calculation. And I'll just say what it presented. It showed a variability in the air water flux that really mirrored the PCO2. There's a lot of outgassing at low salinity and weaker outgassing at high salinity, and in pretty good agreement with what Joshi et al. Found in their 2018 study. So this is my last slide. It's showing a mixing model for the dissolved inorganic carbon, and here we have the apparent dissolved inorganic carbon utilization. This is positive as well. So that also indicates a sink of dissolved inorganic carbon in seawater that could be related to calcification. It's probably more likely related to outgassing of CO2, which will drive the DIC down. So the summary slide here, this is really the first assessment of the full carbonate system in Apalachicola Bay. Prior studies really focused on a single variable. pH and total alkalinity show strong spatial variability. Total alkalinity and DIC show near conservative behavior, but some indication of net sinks. We found what seems to be a biological control on the partial pressure of CO2. And then finally, Apalachicola Bay is a source of carbon dioxide to the atmosphere. Well, thanks very much.
Okay, so we're going to move on to our next presenter. His name is Harry Mumma. He is from Notre Dame, and he will be presenting Exploring Marine Alkalinity Enrichment in Apalachicola Bay.
We just want to say thank you, Ray, for participating. If we have any questions that show up in the chat, we'll get them to you so you can answer them offline.
Sure thing. Thanks very much.
Hello, my name is Harry. Today I will be presenting on work that me and my collaborators have conducted over the past year and a half, mainly related to marine carbon dioxide removal, MCDR, and specifically in relation to alkalinity additions that we've conducted both in the laboratory and in the field now at Apalachicola. So a little bit of an overview of what we're going to be doing. I'm going to start with a justification for why MCDR or why marine carbon dioxide removal. It's going to talk about some of the additions that we did in the laboratory and what we found, transitioning from the laboratory to the field, and then finally I will be going over some results from Apalachicola. So a little background I'd like to provide, and this in conjunction with what Ray just presented on, I think will provide a nice overview in terms of talking about the natural buffering capacity of the ocean, right? As atmospheric CO2 increases, there is going to be dissolution of CO2 into the marine ecosystem, and the interesting thing about that dissolution is that there's going to be a change in speciation of CO2 when it enters the ocean, and this change in speciation allows the ocean to hold vast amounts of sequestered CO2, which it already does and will continue to do so. And in time, this will allow the ocean to hold the vast majority of anthropogenic CO2 emissions. Of course, these reactions, they're going to take place on a geologic timescale as opposed to a human timescale. So over the course of thousands, if not tens of thousands of years, as opposed to the oncoming climate crisis, where we don't have that luxury of time. So this entire research question was motivated by, are there ways to speed up this sequestration of atmospheric CO2 into the ocean? So there's this paper from Renforth and Henderson 2017 that kind of introduced ocean liming and kind of went over the general mechanisms behind how you can dissolve minerals within the ocean that could eventually lead to a sequestering of CO2 into the ocean. And so for our purposes, we decided to focus on lime and portlandite as our minerals of choice, mainly because lime and portlandite, also known as lime and slack lime or hydrated lime, are readily available. They're the product that they come from. Limestone is all around the world, and they are the main principal components behind cement production and therefore concrete production worldwide. So we like the fact that there's so much of it available, and the reaction displayed seemed to indicate stoichiometrically a drawdown of 2 moles of CO2 per mole of calcium added to solution. And so then we got interested in the question, okay, so in laboratory testing, are we able to see a similar drawdown? Yeah, and so I will be going over a little bit of the reaction mechanism and kind of explaining it through the lens of what we have pictured here as a Buren plot, which kind of shows at standard, I would say sea level, standard oceanic conditions that this Buren plot is representing, kind of like changes in the speciation of the carbonate system, and then other players in kind of the alkalinity of the ocean. But at standard ocean surface seawater pH, right, the principal component is is bicarbonate, which has been mentioned, and then there's some dissociation as well into the carbonate ion, and then a little bit of PCO2, or yes, dissolved CO2. So if we look at the reaction, right, this calcium hydroxide is a strong base. You'll have complete dissociation as long as the solution is not saturated into its calcium ions and hydroxide ions. And then this will raise the pH of the solution. But of course, kind of what we talked about before, like, you know, there's also the hydroxide equilibrium that we have to consider. So as hydroxide ion concentrations rise, it perturbs the equilibrium, and weak acids in the ocean will donate protons to the hydroxide ion. This will lead to a repartitioning of the carbonate system, and you will end up converting some of your weak acids in the system to their conjugate bases. And in this case, you'll have go from bicarbonate to carbonate. And so that will drive the pH of the system up, as well as changing the speciation of the system. So you'll have an initial bicarbonate carbonate ion concentration, and at the new pH, you'll see a decrease in bicarbonate ions and an increase in carbonate ions. Important things to note, this repartitioning happens before gas exchange. It is actually what drives gas exchange, because you will have a depression in your PCO2 on the surface. And at the surface, if your system is at equilibrium and your concentrations are relatively stable in your atmospheric and surface ocean water, then you will see if you see a suppression of aqueous PCO2, that will result in a drawdown or an influx of CO2. And then that influx in CO2 will react with carbonate ions, driving up pH. And so will this result in a 2 molar drawdown of CO2 per mole of calcium hydroxide dissolved, is the main question that we wanted to ask. And so now we'll go into our laboratory alkalinity additions. So in the laboratory space, we were mainly measuring this flux through this LICOR 8100 system, which is interesting because you have an environmental chamber, or like an environmental experiment, a controlled contained experiment that exchanges readily with the surrounding atmosphere. But then at certain times, this dome comes over, sits on top, and basically cuts off that exchange with the atmosphere, and then measures the exchange of gases, or I should say the change of concentration of gases within the headspace of the dome for a specified amount of time. And then after that time interval is complete, it can calculate a flux for you. And yes, basically give you an exchange rate of different gases in the system. So we're using this in combination with a pH sensor, a pump that we're at circulation, or like mimicking K value or wind speed. And then we also had a salinity probe, but it was a tiny little thing, and you can't really see it that well from this photo. So in terms of the experimental design, we took DIC and total alkalinity bottle samples before, during, and after the addition. Seawater was from the North Pacific off the Aleutians for this primary experiment, or for, I should say, the first experiment. And we equilibrated 5 liters of seawater with the atmosphere. And after equilibration, we added 15 milliliters of saturated calcium hydroxide solution, which was about 350 micromoles of calcium that was added to the system. And so here are some of our results. As you can see, the x-axis is time in days. The 0, 0 mark is the time at addition. And then the y-axis reports the CO2 flux, as well as the pH. And pH is the green plot, where the CO2 flux is the blue and gray. And so it's very interesting because after addition, right, we have a CO2 flux into the system that represents the change in the headspace concentration, so that the flux is happening into the system, as well as the jump in pH and a leveling out of pH above the starting pH value. So change in the speciation of the carbonate system. Other fun things to note, just to go back and check our theoretical understanding of what's happening, right? We see the pH jump and the pH increase, aka the shifting of the carbonate system, happening before gas exchange. So that shifting and suppression of aqueous PCO2 then allows for gas exchange to happen. Yeah, so I kind of touched on this from our calculations based on the flux rate method. We were able to calculate that we were able to sequester around 1.4 moles of CO2 per mole of calcium hydroxide added. Okay, so, but in terms of transitioning to like field experiments, it's very difficult to directly measure gas flux rates in the open ocean. And so we have terms and we have ways to measure this instead using what is known as the gas transfer velocity, or K. And so K and the difference in aqueous PCO2 and atmospheric PCO2 can give you the CO2 flux and of the system, and it's a proportional measure to wind speed. And so for our experiments and for our purposes, we calculated K to be around 7.5 centimeters an hour, which would be equivalent to wind speeds between 4 and 5 meters per second. Yeah, and so like this is really this is an important thing to keep in mind and notice, because the K value is proportional to the CO2 flux rate. You know, if you have larger Ks, you will see a greater CO2 flux. And so if you're making up that differential in PCO2 between the atmosphere and the surface ocean, right, if you have greater flux rates, you'll make that up in a quicker amount of time, which is important to note because of residence time in the mixing layer for our added alkalinity. And in terms of like thinking about the time consideration in this reaction. Okay, so we'll be transitioning now from the laboratory to the field. So a little note, we initially wanted to try a field addition of alkalinity and then measure basically the change in the carbonate system as a result and the change in alkalinity as a result of that addition. And so initially we were trying, we're talking about trying it in the open ocean or Pilot's Cove, but what we tried at Pilot's Cove didn't really work out because we were doing a rhodamine tracer addition, and it was just too windy and the rhodamine tracer would get dispersed too quickly. And so it was very, very, very hard to track the parcel of water in those locations. We moved more inland to the East Bay, which provided a nice place where we could actually end up tracking a parcel of water. And so we did 2 additions at this point at Annais Dock on East Bay, I should say. So a little bit of a background. The first ejection we did was an addition that we made in East Bay, where we've had a 2,000 liter bladder that we filled with estuarine water, and calcium hydroxide and rhodamine tracer were added to the bladder. So we targeted an analogous addition over our injection site, I would say, which was about 200,000 liters of water we were shooting over, or a surface area of around 100 meters squared. So we were looking for like about 3 milliliters of saturated solution per liter of that 200,000 liters. So that calculates out to around, we needed to add 700 grams of calcium hydroxide to the bladder, and 700 grams would be under the saturation limit, which we could confirm by measuring the pH in the bladder. And that's what we thought. We had a pretty stunning visual addition. Thank you to everyone who helped along the way. Here we have pictured 2 of the team members doing the addition, and Sam and Emily filling the bladder. And yeah, and then here is kind of the results. Very visually stunning. As you can see, the rhodamine tracer kind of spreading out over the East Bay, and our team following and taking samples along the way. Unfortunately, we ran into some, I would say, issues during the first injection, I should say, and we didn't see the PCO2 suppression that we were kind of hoping for, the change in surface PCO2 of the water, and that was mainly due to the low alkalinity of the bladder solution, only about 958 millimoles per liter, which is even lower than what Ray was showing as measuring from that location, or calculated from that location. And we generally think this is because we had some calcium carbonate precipitation within the bladder itself. We didn't mix it that well, and as a result, there was some precipitation out, so some taking out of the alkalinity from the solution that then we didn't end up delivering to the system as a result, and having that alkalinity increase in the system. But we tried a second injection at East Bay with a 5-gallon bucket, where we did the same kind of experiment, just at a smaller scale. And then I went, and instead of having a boat, I actually went and physically walked through the plume with a YSI as it passed over a benthic eddy covariance system. And so here is me getting ready to walk through the plume. Just a confirmation, yes, I did walk through it. And yeah, I will share some of our initial results, including our total alkalinity that we measured within the system that day. And we see the spike in alkalinity after the addition of the calcium hydroxide solution, as well as the spike in pH. It's interesting to note that the pH that we reported here was already pretty high. And so it's interesting to note that our addition works even at higher pHs. And then the suppression of aqueous PCO2 that we talked about earlier. Yeah, and so yeah, those are our initial results from these experiments, and there's a write-up on what we did in Science magazine if anyone wants to check it out. But we had been hoping to do this edition in the open ocean because this is where we feel what we were targeting based on our laboratory experiments. But we were unable to. But we were able to collect seawater from Apalachicola and then rerun it in the experiment that I previously mentioned in the laboratory. So we were able to take seawater from Apalachicola and rerun the experiment, and we got pretty similar and pretty impressive results where we see the pH increase and leveling out at a higher pH, which seems to, negate the effects of ocean acidification as well as a net drawdown of CO2 as a result. And yeah, so main takeaways, I would really hammer home that the addition of calcium hydroxide, increases the overall alkalinity of the system, repartitions the existing carbonate system, which leads to a pH increase, results in a lower aqueous PCO2 if you're in equilibrium with your atmosphere, which will then lead to a CO2 drawdown. And we ended up having an ending experimental pH, which was greater than the initial experimental pH, kind of negating the effects of ocean acidification, and that the drawdown is dependent upon the pH shift in the system or the shift in the carbonate system. I think those are the main things I want to hammer home from this presentation, and I will open it up to any questions.
Thank you, Harry. If anyone has questions for him, they'll please direct them to the page so he can answer them. But our next presenter is Dr. Luca Teliska, and he's also from Notre Dame, and he will be talking about linking performance of calcification of a key ecosystem engineer, development of in situ metabolism and calcification oyster mesocosms.
Thanks, Ethan, for the brief introduction. So this presentation is going to be mostly a methodological presentation. So I'm going to talk about a novel mesocosm approach we've been developing in collaboration with Wade McGillis and Brandon Leslie at Columbia. This can be used to measure continuous variations of oyster performance in the field. So this is just a brief outline of the presentation. I'm going to start with some general background about environmental change, study locations, and model organisms. Then I'm going to explain very briefly again the light-dark bottle method to measure primary productivity, since that's the theoretical basis of our mesocosm functioning. Then I'll go through some sketches about mesocosm design and the way it records the data. And in the end, I'm going to show some initial results, their applicability, and some future plans for the system. So this is just a very general introduction about environmental changes. So we know that our world is changing, and since the Industrial Revolution, temperature has increased, and human activities created new fluxes of carbon dioxide into the atmosphere, leading to dramatic changes in both ocean physics and chemistry, such as the well-known ocean warming and acidification. And these interactive environmental stressors, on top of increased anthropogenic impact in the coastal area, are having dramatic effect for a set of organisms, their physiology, population, community dynamics. And among these organisms and among the species that are mostly impacted by these changes, we have marine calcifiers. So we well know that marine calcifiers are all those organisms that can produce biogenic calcium carbonate structures, such as calcified shells, skeletons, and that usually play key ecological roles for healthy ecosystem functioning. So among the ecosystems that are most sensitive to rapid changes, we have estuarine ecosystems. So estuaries, we know that are a transition zone between saltwater and freshwater environments, and here salinity gradients are a dominant feature that determines species presence and distribution. Moreover, salinity is controlled by a complex set of factors such as riverine input, wind patterns, tides, rainfalls, and changes in only one of these can have dramatic effect on salinity gradients and so biotic assemblages. A good example of this, actually, unfortunately, is what happened, in Apalachicola Bay, that in the last decades, It's been characterized by rapid decreases in rapid over decades decreases in river input, increase in salinity, which had arguably influences on biotic and abiotic alterations, and something that oysters don't like. And so what happened essentially that there was a dramatic decrease in oyster abundance that escalated in oyster restoration project, and also the ban to wild oyster harvesting to favor population replenishment. So our study species is the oyster Crassossia virginica, also known as the Easter oyster. This is a key foundation species that play many important ecological and economic roles. It is characterized by a wide distribution along the North American margin. It's also an economically important species for local fisheries and aquaculture. It's an ecologically important ecosystem engineer that can build intertidal and subtidal reefs, and that provide a wide range of ecosystem goods and services. For example, oyster reefs can protect the shoreline from erosion, storm, sea level rise, and they can also improve water qualities through the nitrification and filtration of sediment particles. As I said before, oysters now are subject to intensive restoration effort. However, there are still many questions that remain about the potential impact of these multiple emerging stressors on both wild and restored oyster populations, and our ability to recover the associated ecosystem goods and services. So the problem is that so far, most of the predictive models about biological responses to change originate mostly either from highly controlled laboratory experiment or field observations. But there is not a great abundance of controlled observations in natural environment, which are essential to translate experimental models to natural population and communities. However, this is kind of being solved today by recent mesocosm approaches that offer a new way to look at species in the natural environment under control condition, so they can kind of bridge that missing link between field surveys and controlled laboratory experiments. And mesocosm in this case for oysters offer a great way to study variations in their performance under rapidly changing habitat, and so the possibility to get information to improve current predictive models. So okay, this was general background. Now I'm gonna talk about the light-dark bottle method approach to measure primary productivity. I'm pretty sure that most of you, if not all of you, knows this, but we need to spend a couple of words about this basic methodology, just because this is the theoretical basis of our mesocosm functioning and design. So it's like being back to classroom now. So if we take, let's start with the black bottle, the dark bottle is kind of easier. So if we take a volume of seawater that contains phytoplankton, zooplankton, and bacteria, and we put that in a dark bottle that does not allow sunlight in, we have no photosynthesis, so all we have in the bottle is respiration that consumes organic matter and oxygen and produces carbon dioxide. So if we measure the oxygen in this bottle, then we close the bottle, we put it away for some time, and we measure oxygen again, we'll see that the amount of oxygen has decreased, and this is an estimate of respiration. On the other hand, if we take the same volume of water and we put that in a clear bottle that allows sunlight in, we have photosynthesis that produces oxygen, but we haven't got rid of respiration that is still consuming oxygen. So if again we measure oxygen before and after incubation in a bottle, in a clear bottle, what we measure is net primary production, which is the amount of oxygen being produced minus the amount of oxygen being consumed. And if we carry out these two experiments at the same time using same container, volume of water, and incubation time, we can calculate the gross primary production, which is amount of oxygen produced by photosynthesis, just the difference between the two. So this is the method, so far so good. Now, we can extend these methods by adding a third clear bottle with oysters in. So again, in this bottle, we have seawater with phytoplankton, zooplankton, and bacteria. So we still have photosynthesis because sunlight can get in, respiration by the water plankton. But on top of this, we have respiration of oysters. So oysters are consuming oxygen on top of that. So if we follow the same methods as before, the same approach as before, we can just subtract what we get in a clear bottle and from our experimental bottle, and we can measure oyster respiration. Again, this approach, now I've been focusing only on oxygen, but this approach can be used not only to measure oyster respiration, but also the oyster effect on other water quality parameters, such as changes in pH and turbidity. And differently from the light-dark bottle method approach that measures the parameter value before and after incubation, with our mesocosm, we can measure continuous variations of that parameter during incubation. Now, so let's look at the mesocosm itself. So our mesocosm is made of a series of experimental chambers or incubators. Here you have a real picture of that, and here a schematic showing how each incubator is made of a sensor chamber that accommodates sensors from a multi-parameter water quality probe, and a sample chamber that may be either empty in the control chambers or filled with oysters in the experimental chamber, separated by a plastic mesh. And the whole incubator can be threaded onto a water quality probe to provide continuous measurement of different parameters such as temperature, salinity, pH, depth, in addition to other biologically interesting factors such as dissolved oxygen, turbidity, and total algae. Especially these three parameters are quite interesting for looking at oyster metabolism, because this can be used as proxies for oyster metabolic traits such as respiration, filtration rate, so the ability of oysters to remove sediment and improve water quality, and feeding rate as well. Now, so this is our prototype mesocosm. So if you remember what I told just a couple of slides ago, you will see some similarities. So again, the mesocosm is made of three chambers: a controlled dark chamber to measure the effect of respiration, a controlled clear chamber to measure combined effect of respiration and primary production, and an experimental clear chamber with oysters in to measure the combined effect of respiration, primary production, and oyster metabolism, or their effect on water quality. Now, the system is connected to a timed water cycling system that alternates two steps of 50 minutes each, or whatever amount of time we want to set the steps to be. And there are two steps. So the first one is a step of incubator flush, during which a seawater pump, an external seawater pump, is switched on and that pumps water into the incubator, and each incubator is flushed. And during this time, the probe sensor measures ambient water conditions. And then there is a second step of closed system incubation, during which the seawater pump is cycled off and individual recirculating pump for each incubator are switched on, providing recirculation separately within each incubator. And during this step, we can measure variations of oyster respiration or water quality during incubation. This is what the mesocosm look like. This is again the schematic we just saw, and here on the upper right we have our prototype mesocosm we deployed in Apalachicola Bay in May 2022, and again the second deployment in the Hudson River last October. And we can see the details essentially. So these are the three chambers I talked about, and they are deployed horizontally on an aluminum frame that holds power supply, the pumping system. And again, here we can see the details of the chambers. So the incubator is made of a sensor chamber, a sample chamber that holds oysters, and this is just an example of a clear control incubator. Now, before showing the result, let's add some color coding here. So now I'm going to represent with blue all the data obtained from a control dark incubator, with yellow control clear, and red the experimental incubator with oysters. What we have here on the right side is just an example of the record we get from the mesocosm for dissolved oxygen. So on the y-axis, we have concentration of oxygen. On the x-axis, we have time, and these are measurements over 3 hours, and the steps were of 50 minutes each. So here we can see I highlighted the two different steps I just talked about. So the shaded areas represent the incubator flush steps, and the white area represent the closed system incubation steps. So from this graph, from this kind of record, we can get two types of information at the same time during the two steps. So during the steps of incubator flush I just talked about, we can get mean value from each of these intervals and get information about temporal variations in ambient conditions. While during the second step of closed system incubation, we can get information on how the analyzed variables change during incubation. So a kind of information we can get is, for example, the rate of change of the parameter of interest during incubation that can be approximated by a regression coefficient from a linear or non-linear regression, depending on the parameters we're looking at, between the parameters value and the incubation time, so 50 minutes. So by the way, so here we were recording at a frequency of 1 minute, so we got 15 measurements for each step. So now let's look at some of the initial results here. So, okay, first, again, these are the two deployments we did. So the first one was in East Point on the pier for the addition experiment you just saw before at the Apalachicola Research Reserve. So the first system was really a prototype system that was also equipped with an independent power supply that it didn't turn out to be enough, essentially. So the system ran for just less than a day, but it ran great. So, I mean, we proved that the methods of adding the 3 chambers were very good at characterizing the response of, water column and oysters. And so we deployed that again, this time in the Piermont Pier in New York, closer to where I spend most of my time now. And this was a complete system. So we had the 3 chambers. I mean, we rebuilt the frame, the pumping system, and this time there was no independent power supply. So we just plugged in the mesocosm to a power socket on the pier just to be sure that that part didn't fail. But we were shooting for a week deployment. This time we got just 3 days of data because a fishing line got stuck into the pumping system. So, but for those 3 days, it worked great. So we learned a couple of things to improve for the next time, for the next deployment. So these are some initial results. Okay, it looks a lot, but I'm going to talk you through this because what we have essentially on the left side, these are the full set of parameters we can measure during incubation, not during incubation, we can measure during the step of incubator flush. So these are essentially ambient conditions and how they change over 3 days. So remember the color coding I told before. So blue is the dark incubator, yellow is the control clear, and red is the incubator with oyster. And here we have just changes of temperature, salinity, depth, dissolved oxygen, turbidity, pH, and total algae or chlorophyll A. So you can notice that for chlorophyll A, we are missing the the blue signal, so the control dark, just because we run short of sensors. We didn't have enough to equip all the chambers, and I decided to put that on the clear and the oyster one. So the interesting results are the one we have on the right. Essentially, these represent changes of the changes of our parameter during incubation. So if you remember what I talked about before, so these are essentially a rate of change of parameters during those 50-minute incubations over time. Okay, for dissolved oxygen, turbidity, pH, and chlorophyll A. I mean, actually, we can see from this result that the mesocosm is doing a great job at showing the relative contribution of respiration, primary production, so photosynthesis, and oysters to the different signals. So one good example is, for example, if we look at dissolved oxygen, we can see. So remember, these are regression coefficients. So any value below 0 means a decrease of the parameter's value during incubation. Positive value means an increase of the parameter value during incubation. So here we can see that, for example, respiration, so the dark control chamber is always negative. If we add on top of that, the photosynthesis effect, we can see the day-night cycling of photosynthesis, and then we have the oysters. Obviously, the oysters, this is just the sum of the oyster contribution plus these 2 lines, plus the yellow line. Okay. Then, okay, so we saw that the mesocosm essentially works, or at least we believe it works, and we can get very good data, and it has great potential for doing long-term monitoring of oyster metabolism in the field. But something we can use this data for is, for example, to develop models to understand the ecosystem goods and services of oysters under changing environmental conditions. For example, we can get information on how oysters are going to improve water quality when estuarine conditions change. So we can model, for example, their ability to decrease turbidity during incubation, which I'm going to call here oyster's filtration capacity. So what I'm plotting here are essentially the changes in turbidity with changes in mean ambient conditions for turbidity itself, dissolved oxygen, and pH. Again, these are just data for 3 days, so it's not much, but we can already see, for example, by looking at the turbidity change with increasing turbidity itself, is that the oysters are doing a better job in cleaning up the water compared to the control chambers. And we can see also there are clear changes with dissolved oxygen levels and some fluctuation with pH. I mean, this data might be very interesting to get more data on this, and it shows us the potential of the mesocosm to get information to expand current predictive models of oysters filtration capacity with predicted, estuarine, hypoxia, or acidification. So these were some initial results, and then now in terms of future plans, we've already planned to redeploy the system again in May. So in just a few months. Before that, we're gonna make some improvements in general to the pumping system and redesign the support platform just to be sure that it doesn't fail after a couple of days this time. And so deployment is going to be again in the dry barn of Apalachicola Bay. Now the tower, this is just an old picture of the tower. Now, I mean, we're going to have a power supply there, potentially a meteorological station. And at the same time, we're going to also collect discrete water samples to measure DSC total alkalinity and make estimations of oyster calcification within the incubators. And yeah, this is just the acknowledgement. So I would really like to thank all the collaborators at NERRS, Columbia University, and Notre Dame University, and all the people that helped out to make this mesocosms a reality. And that's all for me. Thanks for your time.
We've got some time for some questions. Does anyone have questions?
There's one hand raised from Wade McGillis online, but it may have been for this presentation before, so I'll go ahead and unmute Wade, and you can unmute yourself if you have something you want to ask. So we've got a question from Duncan Moment. So I'm going to unmute you, Duncan. Feel free to go ahead and unmute yourself.
Can you guys hear me now?
Yes, I can hear you.
Okay, nice. Thank you. I really enjoyed this. So my question was related to, I believe you mentioned the assimilation rate of oysters and being able to monitor that with this system.
Mm-hmm.
I just wanted to ask you, I thought you mentioned chlorophyll A on the assimilation rate slide, so I just wanted to ask how the system transforms the rate or the amount of chlorophyll A into assimilation in the oyster, if that makes sense. Like how are the two being related to each other?
So, what do you mean by assimilation rate? So it's okay. Which slide? Do you remember which slide? I mean, you were.
Yeah, it was on the slide when you were mentioning about being able to look at like filtration with turbidity, and then some factors you can measure.
So, keep on, and keep on. Oh, this one. Okay.
Yeah. Okay, so it was the feeding rate. I'm sorry, I thought it said assimilation rate.
No, feeding rate. Yeah, I know. Yeah, okay. No, this feeding rate and that's filtration. I mean, though they're filter feeders, but yeah, they are selected for the filter. So that's, I mean, that's the key thing. I mean, here, I mean, I just wanted to stress, I mean, we tried, I mean, let me go first to a couple of results, because this is something that, I mean, when we plant the mesocosm in the beginning, obviously we know that oysters are filter feeders, so I mean they kind of filter whatever is in the water column, though they have this ability to filter out some particles depending on size, and some of sediment is dropped in the chamber as pellets. Some of the rest goes through the stays there, but they have this ability kind of to filter out some particles compared to the others, and that was kind of very interesting. I mean, just by looking at, for example, the rate of change here. So if you notice like variability in turbidity and chlorophyll A, you can notice that, I mean, there is some kind of difference in response. I mean, here I'm just assuming, I mean, these are again just 3 days data from 3 days, but I'm assuming that, I mean, this is also a very nice way to potentially understand, I mean, their ability to, discriminate what they're filtering. I mean, they can already do that, but this is a kind of nice way also to depict that, essentially. But yeah, I mean, the ability, their filtration rate here, I mean, it's still, yes, there is potential to measure that, but it needs really more testing before making stronger assumptions on that. I mean, but yeah.
Gotcha. Yeah, that makes sense. Thank you. This is really interesting. I appreciate your answer and your talk.
Thanks.
Thank you, Luca.
Thank you.
And now I'd like to present our next presenter, Dr. Jill Ariola from Penn State University. She will be talking to us about improving estimates of ecosystem metabolism rate, a controlled volume approach in Pilot's Cove, Apalachicola Bay.
All right. Hi, everyone. Thanks, Ethan, for the introduction. It's so great to see my collaborators, even though I couldn't be there in Florida. It's probably nicer there than it is here in central Pennsylvania. I'm going to talk to you today just briefly about some work that we've been doing down in Apalachicola Bay over the past couple of years. I'm going to talk pretty heavily about our methods and the deployments we've been trying to do down there, and just some preliminary results. So the open water method has been used since the 1950s to look at ecosystem metabolism rates in rivers, lakes, and the open ocean, and more recently in estuaries. Using diurnal variations in the oxygen concentration, as you can see here, of a well-mixed water column, we can estimate metabolic rates using an oxygen mass balance framework. And so here's that framework at the bottom. So we have our oxygen concentration is the balance of GPP, gross primary productivity, respiration, and then abiotic processes as air-sea gas exchange and lateral advection, which you can see down here. So air-sea gas exchange, as Harry mentioned before, has to do with the gas transfer velocity over the height of the water column multiplied by the oxygen saturation deficit. And then lateral advection is the gradient of oxygen in the U and V direction. And when we talk about net ecosystem production, sometimes also called net ecosystem metabolism, that is just the difference between primary productivity and respiration. With estuaries, studies have found that lateral advection is hard to quantify. A lot of people don't quantify it, so it's often ignored, and that can lead to some challenges in the metabolism estimates. So for example, here's a study that was done in 2014 by Caffrey et al., where they looked at seasonal and interannual patterns of metabolic rates across the Northeast Gulf of Mexico. Here we have Apalachicola, where they looked at East Bay, Cat Point, and Dry Bar. And they found that 5 to 24% of the results across their sites were unrealistic. And when we say unrealistic, we mean that GPP was negative or that respiration was positive. And they theorized that this is the effect of lateral advection, either by tides or by wind, and the smearing of that diurnal variation, or the DO time series. And so when I'm talking about the effect of lateral advection, especially by tides, this is kind of what I'm talking about. So this is just a little cartoon simplifying a dissolved oxygen time series for a day and what the tide is doing. And here, so the tide's going up and down. And when the sun comes up, DO goes up. When the sun goes down, DO goes down. That's a very simplified, nice way to look at it. However, it's not always that nice and clear cut. Sometimes the dissolved oxygen time series can actually start to look like the tidal signal. And so to get these estimates, sometimes we get those unrealistic results. So there have been a lot of studies trying to improve metabolism estimates using modeling. This is an example from one of our collaborators, Marcus Beck, that they did in 2015, where they looked at removing that tidal advection signal from the DO time series using a moving window weighted regression. So this is from their paper. At the bottom figure here, you can see just the tidal cycle over a period of several days. The yellow bars here indicate when it's daylight. And so what they found is this blue line is actually the observations in dissolved oxygen. And it mimics really well the tidal signal, which it shouldn't be doing. So they filter out that tidal signal. I'm not going to explain it now. You can read the paper. But then they result in this nice, more diurnal curve is what we expect. However, modeling like this hasn't yet been validated by field measurements. And really, to hone in on metabolism estimates and improve estimates through modeling, we need to quantify all these fluxes of oxygen in 3 dimensions. So including the air-sea gas exchange and also including lateral advection. So that was kind of our goal, is to do all these measurements at once to improve models of estuary metabolism. And we're going to do that through a control volume. So for those of you that don't know what a control volume is, think of it as just a wedge, kind of like as cheese cut out of an estuary. So there are 3 vertices. Here, this light blue is the surface of our wedge, and then we're looking through one of the sides. So 3 vertices create a triangle. And we can quantify the advection of oxygen through each sides of this wedge or the triangle, while simultaneously calculating the gas flux velocity through the air-sea interface. And that will allow us to close that oxygen budget with, including these parameters, these measured parameters, and that will give us a better idea of GPP and respiration, or those metabolic rates. So here's just a little cartoon of our idealized control volume. Just think of it as out in Apalachicola Bay, where we're going to have instrumentation at our 3 vertices on the bottom. That includes water quality parameters, which I'll discuss in a second, current profilers, and then what I don't show here is the tower that's going to be doing our air-sea gas exchange measurements. So again, I'm going to show you today preliminary results of dissolved oxygen time series and currents that we measured in our control volume at Pilot's Cove. So we've tried a few times to go down there. It's not awful to travel down to Florida, so I don't complain too much. But we do 1 control volume for a month on deployment every time we go down there. Here's what our lander looks like. In the right, there's Scott holding our lander as about to go over. You can see that we have water quality measurements that we take at 2 depths. So we have 2 YSI multi-probes, one that's looking up and is reading about 1 meter off of the bottom, in the water column, and then this one that's more parallel, and that's reading about 20 centimeters of water quality off of the bottom once it goes overboard. Next to each of these landers at each of our vertices, we are going to have an ADCP, or an acoustic Doppler current profiler, and I'll explain that a little bit more detail in a second. And then to get the air-sea gas exchange, we also need to water PCO2 in the water. And then on the weather station, we need to get the atmospheric measurements, wind speed and direction, and PCO2. So ideally, all these things would be deployed at once. So we tried dry bar first in November 2021. We learned a lot of lessons. We learned that dry bar is not a great environment for our landers. They actually sink into the mud out there. We learned that our weather station was underpowered, so unfortunately we couldn't get the air-sea gas flux measurements. And at the time we didn't have 3D current profiles at each vertex. And we realized if we want to quantify the lateral fluxes through the sides of our volume, we're going to need those measurements. We went back in May of 2022, so last year. This time we moved to Pilot's Cove. We chose that because that's a seagrass benthic habitat. It's also sandy, so our landers won't sink. Again, we didn't have the weather station or water PCO2, so no air-sea gas exchange. We did put out 3 ADCPs. Unfortunately, the one close to the tower at Pilot's Cove, which you can see here in this picture, was tampered with. There's evidence in the data that it was taken out of the water by someone and put back down upside down, which you can't do current measurements when it's upside down. And also at one of the other vertices, one of our ADCPs only collected 2 weeks of data out of the month. So we're still having some gaps in our idealized control volume. We tried to go back in November 2022, and we just happened to pick the week that Hurricane Nicole came through. She was a tropical storm by that time, so nothing got deployed. But we're planning on going back in May. I'm very excited to come back down. Hopefully this will be a full shebang. This will be a full deployment. We can get air-sea gas exchange. We can get the lateral fluxes and get them all measured at one time. So I'm just going to show you some of the results really quickly from our May 2022 deployment at Pilot's Cove. So for those of you that aren't familiar, so here's a map of the reserve in the upper right with some of the major stations. Pilot's Cove is down in the southern part of the bay here. This is just a Google image showing where our points are of our volume. So the tower was 1 point, and then we have another that we call west, and another one that we call south. The distance between our stations ranged between 140 meters to 165 meters. So this is a small volume, in relation to the size of the bay. Average depths, so taking the mean depth of the entire month that they were deployed, the tower and the west station were about 2.7 to 2.8 meters of depth. The south station was shallower at 1.5 meters. And you can see even in this image how it's starting to shallow up as it approaches the island here. I'm not going to show you all the water quality data because there's a lot of data that was collected. This is just some examples of data that we collected. This is from the west station. So because we have 2 probes measuring all the water quality, we have deep, which is this black line here, and then we have surface, which was a meter off of the bottom. So when I say surface, it's not really surface. But you can see that we captured both the spring and deep tidal cycles over the month. Looks pretty good. They're very similar. Temperature for the surface from the bottom at the west station didn't vary a whole lot, between the surface and the bottom, except for this period here in around June 7th and 8th, which is interesting. And then when we looked at our conductivity, we realized that conductivity at the deeper sonde, which is only, about 80 centimeters from the other one, was almost always higher, which means that this is stratified. If you remember back to like my first slide, I said a mixed water column. This indicates that the water column, at least during this time at this station, was stratified, which makes trying to estimate metabolism a little bit tricky. So here's the dissolved oxygen time series. Now you're looking at results from all 3 stations. So we have the tower at the top, the west station in the middle, and the south station at the bottom. And just to throw this out there, you may notice one is missing here for the west. There was an electrical malfunction with the sonde, so unfortunately we don't have the surface DO measurements. But what you can see if we just focus on the tower here, surface DO was almost always higher than at the bottom. So again, indicating that this is a stratified system. And then going back to that, I mentioned that temperature difference around the 7th. we see large variation between the bottom and the surface in terms of oxygen for a few days, to where the bottom, is almost anoxic, and it's a seagrass habitat. So that's kind of interesting and surprising. We suspect that also happened here at the West Station. You don't see that here at South. Again, it is more shallow, but it is still stratified. We just don't see as large of a difference. So this is wind speed and direction that's measured at Pilot's Cove. The Department of Environmental Protection has a station out there that continuously measures this, which is great. Although we are planning on putting our own weather station out there. But this is just 2 weeks worth of the wind. And the only reason I'm showing you 2 weeks as opposed to the month is because one of our ADCPs only covered 2 weeks. And we want to compare apples to apples when we're trying to understand what's driving the lateral infection of this control volume. So this red dashed line here is the mean. So it was around 10 meters per second for the first 2 weeks of our deployment. And this wind rose is just also the 2 weeks, just showing that the dominant wind direction was southeasterly and westerly, and the warmer colors here indicate higher speeds. So the higher velocities or the higher speeds were out of the southeast direction in terms of wind. Okay, so I mentioned current profilers that I would explain them. This is our volume once again. Now we're in space and we're looking down on our volume. Again, we don't have results for the tower. Here's our west station and our south station. And I just remember that these are only 140 meters apart from one another. And when we're talking about profiles, we're talking about vertical profiles within the water column. So the ADCP looks at velocity and direction in 3D at every 3 centimeters for 35 bins. So from the surface, or I'm sorry, from the bottom up, it looks to about 1 meter and 15 centimeters, 1.15 meters. I'm not going to show you every single bin. That's just way too much to look at. But I will show you a few for the west and the south station, so you can just get an idea of what the currents were doing for the first 2 weeks of our deployment. So starting with the west station. So here, this is 55 centimeters off the bottom, 85 centimeters off the bottom, and then 1.15 meters off the bottom. Again, warmer colors indicate higher speeds. And this is just for the 2 weeks. It's similar to a wind rose, but now we're looking at currents. You can see at the west station, the dominant current, regardless of whether we're close to the bottom or higher up in the water column, was coming from the south, which maybe it's wind driven, but we're not seeing that westerly effect that was dominating also in the winds. At the south station, it's a little bit of a different story. Again, these are only 140 meters apart, but it is more shallow. So at the same depths, we're now seeing more of a southeasterly current flow. And as we get shallower in the system, we actually start to see more of a back and forth, whereas at the west station, we don't see that at all. There's a lot more work that needs to be done to figure this out. There's so much data, and I haven't had time to go through it all. It'll be really interesting to start picking up out where this is tidally influenced or winds. Speaking of tides, so there was a study that was done in 2002 that looked at the average 25-hour tidal flow, I think from a year's worth of data in the 90s, but they did find that the average tidal flow for Apalachicola Bay dominated from east to west. And so this yellow star is our site. And so, the current will start to flow along the barrier island there, but still in an east to west direction, which we didn't observe in our current meter measurements. Just looking at speeds, so this is the south station in the dots and the west station in the triangles. This is all those 35 bins looking up in the water column. And this is just the means for the entire 2-week time series that we were looking at. You can see here that speeds kind of capped out at 90 centimeters at the south station, and it started to decrease. We don't see that at the west station. Now remember, the south station is about 1 meter more shallow. We did verify that the beams were close to the water surface, but did not exceed the water surface. So what we think is this reduced speeds that we're seeing at the south station could actually be due to wave action or possibly winds. A way to look at this in the water column. So here's our south station, and here is our current speed profiles. So what's happening is speed increases as you move away from the bottom and then decreases as we get close to the surface. We don't see that at the west station, but we think that's probably what you observe if we could see higher into the water column. The ADCP is limited, but we would start to see a decrease in the speed as you get close to the surface. So for our next steps, we're going back, as I said, in May of this year, and we're going to try to do everything. I hope it happens. It would be great. We also need to understand a little bit more about the volume, and bathymetry is a little bit different, station to station. So fortunately, the NERR has gone out to measure bathymetry for us for the volume. We still need to validate the other methods to remove the tidal advection signal using our field measurements. And just to throw it out there, we are creating our own model to estimate metabolism for estuaries. It's called eBase. So please check it out if you're interested, and we would love to hear from anyone that gives it a go with some of your data, and please let us know what you think. So just briefly to summarize, lateral advection is often ignored, and it can potentially lead to unrealistic metabolic rates. So using a control volume, this allows us to close that oxygen budget by measuring everything simultaneously. We found that the shallow water column at Pilot's Cove is stratified most of the time, which is not ideal when we're trying to estimate metabolism. Current speeds in the direction at the west and south stations do differ from one another. We need to dig into the data a little bit more to figure out why. And our findings will be used to validate that weighted regression method to remove the tidal signal. So I just want to say thank you to NSF, and then also a big shout out to everyone at the NERR that has helped us, especially Ethan, Sam, Michael, Scott, and Megan, and our collaborator, Marcus Beck, at the Tampa Bay Estuary Program. Thank you.
Thank you, Jill. Do we have any questions?
Hey, Jill, this is Jake.
Hi.
Do you have any ideas about how we're going to get around this, this stratification problem? I mean, we're in 3 feet of water and we're seeing big changes. I mean, next to the sampling during hurricanes, when it's well mixed.
Yeah, we tried that, remember? Yeah, so what we could do, it's something that we have discussed here at Penn State, is, instead of using a 1-box model, we split the volume into 2. And so we'd have to, use a bottom model and then an upper model, because, they are so different, and, maybe we'll have 2 metabolisms. So it's going to be a little bit more complicated. It's going to take a little bit more thought. I anticipate we'll see stratification again when we come back in May. So I think a 2-box model might be the way that we have to do it.
Gotcha. Thanks.
Thank you, Jill. Welcome back from break. My name is Sam Lucas, and I'm a member of the research team here at the Reserve, and I will be introducing the next round of speakers for our final session of the day. All right, and our first speaker is Pakin Asawapaniwat from the University of Florida, and he will be presenting changes in controls of carbon burial in sediments experiencing mangrove invasion of salt marshes in Apalachicola Bay coastal wetland. Can you take it away?
Good afternoon, everyone. Today I'm going to present about changes in control of carbon burial and sediment experiencing mangrove invasion of salt marsh in Apalachicola Bay coastal wetland. And before we start, I would like to express my gratitude to all source of funding from Sean and Barry Thompson's Endowed Chair of Geological Science, as well as I really need to thank all of the Bright House members for helping me during the field work and sample collection and pre-treatment. So in general, vegetated coastal wetland is an enormous stock of organic carbon in the coastal ecosystem. It accounts for as high as 50% of organic carbon burial in marine sediment. And in this vegetation community, the dominant plants are mangrove and salt marshes. These 2 groups of vegetation can have different roles in controlling organic carbon stock in this system. And most of the previous publications provided observed that there is higher organic carbon stock in mangrove compared to salt marsh. And in both of them, most of the organic carbon were stored inside in the sediments. That is why a lot of publications trying to measuring how much organic carbon is in mangrove and salt marsh sediments and comparing their organic carbon burial rate. And most of the previous literature report that there is higher organic carbon model rate in mangrove sediment compared to salt marsh. And one of the reasons can be attributed to the native properties of mangrove organic carbon. That mangrove is a woody vegetation, so they have more recalcitrant organic rich component that could be strongly preserved in the sediments. However, for the salt marshes, the materials are more labile, so they could be easily decomposed and transformed to carbon dioxide and then released away from the coastal wetland. And if we want to talk about the carbon storage in wetland, one major factor that we need to discuss about is the presence of oxygen in the system. And first of all, if you have a lot of oxygen in the system with the high oxygen availabilities, this thing could promote the activities of aerobic microbes. And this guy could decompose organic carbon, transform them to carbon dioxide, leading to the carbon loss from the system. However, in most of the wetland where the water have flooded, the oxygen could be absent. This could lead to the preservation of organic carbon under this anoxic condition. Nevertheless, there is another mechanism that could lead to the protection of organic carbon in the oxic condition, which is the interaction between organic carbon and iron. So basically, iron plus 2 is the aqueous form of iron, but with the reaction with oxygen, iron could be oxidized to iron plus T, which is a solid phase. And this phase could interact with organic carbon and precipitate together as FeROC, or the thing we call organic carbon reactive iron association. And this one could like protect organic carbon from microbial attack and enhance the stability in the oxic conditions. The reason about why I need to talk about all of this process is that if we have coastal wetland vegetation such as mangrove, this vegetation could have some oxygen leakage from the rhizosphere. And the oxygen right here may promote the formation of oxic microenvironment in this sediment. So my main research question is that will all of this oxic process being captured in this oxidizing rhizosphere? And to be more specific, in Apalachicola coastal wetland, there are 4 major vegetation types: black mangrove or Abyssinia germinans, red mangrove or rhizophora, and Juncus and Spartina salt marshes. According to the previous literature, mangrove tend to produce larger amount of recalcitrant organic carbon compared to salt marshes, and black mangrove may produce largest oxidizing rhizosphere comparing to Spartina salt marsh and red mangrove respectively. So the reason why we need to discuss about the different effects of vegetations on organic carbon preservation is that because nowadays there is less frequent freezing events in Appalachia because of global warming. So mangroves, which are tropical vegetations, are now migrating their habitat range northward, and they are now replacing the salt marsh in higher latitude. So this vegetation shifts is also very interesting in Apalachicola system because Apalachicola barrier island is the highest latitude that you can find both black and red mangrove together on the coast of Gulf of Mexico. So the main idea of my research is to analyze the effect of mangrove substitution of salt marshes on Apalachicola barrier island and its effect on organic carbon model rate and organic carbon source, as well as organic carbon preservation and degradation. So in my work, we start with collecting sediment core from pilot scope regions on Apalachicola barrier island. We collect 12 core and 3 core per each of these vegetation communities. And we analyze for latitude chronologies and organic carbon content to reconstruct organic carbon model rate in this system. And we also identify organic carbon source by using the resi-13 as a proxy to separate C3 mangrove and Juncus from C4 with Spartina salt marsh, as well as we use the lignin oxidation product to separate mangrove woody materials from salt marsh non-woody materials. And we also quantify how much organic carbon is associated with reactive ions. So here is some of my preliminary results. First of all, let's discuss about organic carbon border rate first. And at this point, I only have the data of organic carbon border rate from one black mangrove and one red mangrove sediment core. And what we observe is that the organic carbon border rate among these two vegetation types did not differ that much. It ranged from like 100 to 120 grams of organic carbon per square meter per year. And if we're comparing two of these rate-to-10 profile with the record of mangrove present in this region, what we observe is that the first occurrence of black and red mangrove in this region occur about like in the top 15 centimeters of the core, which is very young. However, when we take a look at the proxy to identify source of organic carbon, we observe that source of mangrove, the presence of mangrove derived material was down to the bottom of the core, suggesting that some of the mangrove may insert some below ground, maybe root production to the sediment organic carbon stock as well. And if you take a look at this profile, you can see that in the green Juncus somas and the blue Spartina somas core, this profile is quite static, suggesting that there is the permanent source of organic carbon from Juncus and Spartina somas respectively. However, in the red and the black mangrove line here, there is a shift in organic carbon source from C4 Spartina somas to C3 mangrove material at the bottom of the core. And we also detect the same vegetation shift by using lignin phenol vegetation index. As you can see that in the red mangrove core, the higher LPVI values at the bottom of the core, suggesting the stronger input of salt marsh. And this value decreased to the top, suggesting stronger input of mangrove in the top of this core. And now let's talk about organic carbon degradation. So the parameter in this profile is acid to aldehyde ratio. So basically, higher acid to aldehyde ratio reflecting that this lignin was oxidatively decomposed, or the aldehyde functional group was oxidized to acidic functional group. So in the top part of the core from 0 to 10 centimeter depth, out of this core has lower acid to aldehyde ratio compared to the deeper section, suggesting that this top 10 centimeter may be dominated by fresh mangrove and salt marsh material. And I interpret that this may be the layer of fresh mangrove and salt marsh litter. However, when we go down from 10 to 30 centimeter depth, and the acid to aldehyde ratio increased a lot, it may indicating that, and then in mangrove core, this ratio decreased back to the lower values below 30 centimeter depth. However, in the two salt marsh core, this ratio remains static and being high to the bottom of the core. My interpretation on this profile is that from 10 to 30 centimeter depth, in mangrove, there is the effect of oxidizing rhizosphere that promote oxic transformation of lignin to have higher acid to aldehyde ratio. However, in the salt marsh sediments, salt marsh material are more labile. In other words, they are easily to be decomposed. So all of them were decomposed to higher acid to aldehyde ratio throughout the entire section of the core. And finally, let's discuss about the iron-bound organic carbon. So in general, this is my sediment sample, and we have two different pools of organic carbon. One is not associated with iron, but the second one is linked with reactive iron. And I performed citrate dithionite bicarbonate reduction experiment to break the bond between iron and organic carbons. So what happened is that these iron-bound organic carbon will be released away to the solution, but the residual organic carbon in the sediment is the pool that is not interacting with iron. So I find a difference in organic carbon content in this and this part of sediment to quantify how much organic carbon is linked with reactive iron. And what I observed is that highest amount of organic carbon that was associated with iron was found in the Abyssinia core and Spartina salt marsh core, which is following our hypothesis that Abyssinia is the type of vegetation that develop most intensive oxidizing rhizosphere. However, we observe that the amount of reactive iron is higher in red mangrove coral or the rhizophorac sediment, despite the fact that this coral has very low amount of organic carbon that's associated with reactive iron. So we can draw a conclusion that red mangrove sediment may be extremely oxidized, but they are less efficient to interact with organic carbon, less efficient in formation of reactive iron associated with organic carbon. And finally, we also take the extracted sediments and analyze for the lignin concentration in that pool. And we compare the amount of lignin in the unbound fraction with the bound sediment. And what we observe is that, first of all, this is the CV ratio. CV ratio is also another indicator to identify the source of organic carbon, and lower CV ratio reflect mangrove derived material, and higher ratio reflect so much derived materials. In the upper section of black mangrove core, we observe low CV ratio in both bulk and iron extracted sediment, suggesting that this region is dominated by mangrove material, maybe in the zone of mangrove fresh detritus. However, when we go down, you can see more clear separation between bulk sediment and the iron extracted sediment. In other words, the gray line is a sediment without iron-bound organic carbon. And what we observe here suggesting that the organic carbon that came from mangrove are preferentially interact with reactive iron. However, the organic carbon that came from saltmarsh, from former vegetation habitat, are not associated with reactive iron. We also plot the acid-aldehyde ratio, which is the degradation proxy between the bulk and iron extracted sediment. And we also observing that the pool that is not associated with reactive iron has higher acid-aldehyde ratio, suggesting that this pool is more oxidatively transformed. So in this figure, my hypothesis is that from 10 to 30 centimeter depth, there is a lot of organic carbon is preserved by reactive iron. The pool that is protected by reactive iron could maintain its fresh signal, but the pool that is not protected by reactive iron was transformed to more oxidized phase. However, if we go down to below 30 centimeter depth, the reactive iron was destabilized in the anoxic zone, so it released back the oxic sediment. Released back the fresh lignin signal down to the bottom of the core. So, and here is my last conclusion of my finding. Organic carbon burial rate in Rhizophora and Abyssinia core was similar, and we also detect the shift of organic carbon source from mangrove to saltmarsh in both core. And we also observe that strong effect of oxidizing rhizosphere that promote the decomposition of mangrove material, as well as we also observing that in the black mangrove or Abyssinia sediment, there is a large fraction of FEROC association. And this is our reference. And thank you so much for your attention. Do you have any questions?
Has anybody done this comparison between mangroves and the salt marsh?
Sorry, and what?
Between the mangroves and, like, say, like the junkies in China?
I will try to do that, but I haven't produced data yet.
Thank you so much.
Thank you.
Our next speaker is Iyong Calvin Kong from the University of Florida, and he will be presenting linking mangrove vegetation and carbon sequestration across the tropical temperate transition zone.
Hello everyone, and hello everyone online. My name is Iyong Calvin Kong. I'm from University of Florida, currently a PhD student with Dr. David Kaplan. So yeah, just last summer we went to the Rookery Bay NERR down in the Southwest Florida to conduct a mangrove study, and they proudly claim that they're the only NERR in the nation that has mangrove. And I sort of stood up for the NERRS that it's not true anymore, and it's not the case. We have the picture of here is St. George State Park with red mangroves and other black mangroves, as Parking has talked about. So this is known as the tropicalization process that's happening with the climate change. Of course, it has brought out a lot of the changes to the ecosystem of coastal wetland, and potentially fisheries and wildlife habitats provided, and also the soil beneath this with carbon and different decomposing activities being impacted. So here we're trying to explore the linkage between the mangrove vegetation structure and also the soil part. So yeah, before we dive in, we just want to pay special thanks to Hannah Seckles and amazing folks here at NERR who have helped us with the field study, and also NCBS of UF and USGS for funding this research. Together, they are making the research possible. So yeah, like thanks for Parking for making this latest great foundation of the talking about the mangrove pole expansion. So I just go briefly here is basically we know as the warming climate has resulted in a large amount of species, tropical species, especially to move into the temperate zone, known as a process of tropicalization, including mangroves here. And we have extensive evidence showing that mangrove areas has been expanding into the northern temperate zone temporally across the globe, including here in Florida. But still, we lack the specific knowledge about how mangrove vegetation, community composition, change and response across the temperature, latitude, gradients, and ecological levels and different species. Okay. So at the same time, we also know that blue carbon, known as the carbon sink provided by coastal wetland, has been under this impact of the changing climate as well. But yet, regarding the question of how mangrove expansion specifically affect the soil carbon storage, is still very context dependent and site specific. So we here are trying to investigate the relationship between the soil carbon storage and sources and the mangrove vegetation structure along this Gulf Coast of Florida gradient. So we specifically focused on 3 research questions. The first one focused on the mangrove vegetation, is how does mangrove community composition and above ground biomass vary with the minimum air temperature? Second, how does such mangrove vegetation gradient affect the soil carbon storage and sources? And third, eventually, how will we be able to inform how the mangrove ecosystem properties continue to change in the future warming scenarios? That's working. So to answer these questions, we conducted gradient research, the field study across 18 sites in the Gulf Coast of Florida, including about 8 sites in the Apalachicola Bay itself. And as the live photos have shown that there's much of the variation for mangrove vegetation itself is very intuitively. And we see that there's many aspects of the vegetation changing with canopy height of the mangrove, percent coverage of the mangrove, so the species composition. So to characterize such variation in numbers, we developed a plot-based methodology to basically place a transect in the lower to middle intertidal zone of the mangroves and place through repetitive plots to characterize the species compositions and also the above ground biomass estimation. We also collect the composite soil samples here down in the corner that characterize the soil properties on the top 20 centimeters layer, which is the most relevant to the question of mangrove range expansion in recent years. So yeah, moving on to our first research question is how does the mangrove vegetation part, community composition, and above ground biomass vary with the temperature gradient? So on these figures, we first figure out that on the x-axis is the temperature minimum that we grabbed from the graded prism temperature data nationwide in US. And on the y-axis are the percent coverage of mangrove and the canopy height of mangrove and how it changed with the temperature minimum. We first found out that mangrove coverage and canopy height show the threshold response threshold response of increase actually with the temperature minimum across this Florida gradient. And at the same time, notably, this threshold zone of coverage is much wider than the canopy height, meaning that the canopy height has a much more sensitive drop here in the higher latitude with temperature. Also, for the above ground biomass, we separate into tall and short stratum of the mangrove trees, and we found out that on the very left figure is the tall stratum of mangroves has been contributing mostly to the increase of above ground biomass with temperature minimum, a linear increase. And also the short tree stratum has not exhibited any relationship with the temperature minimum here, both in terms of the abundance of short trees mangroves and also the above ground biomass per individual here. It's likely due to a population dynamics effect, amid freezing. And for the species compositions, we found out that in North America here is mainly the red, black, and white mangroves here, indicated separately by the color red, gray, and black in the figures. And we noticed that with the temperature changing, tall red and white mangrove trees are exhibiting a linear increase relationship with the temperature, both in abundance and in percent coverage. But at the same time, interestingly, the tall black mangrove trees are showing a quadratic relationship, meaning that on the both end is separately dominated by the salt marsh or the red mangroves, and it only peaks in the middle of it. Sorry. Okay. Yeah, here are some photos showing that the black mangrove dominance and the red mangrove dominance, different photos, and you can see there's very pronounced differences in the structure of it, and also the above-ground biomass is different. But it's likely this result is likely to imply for that the mangrove pore expansion process, it might be following a successional stage changes with the most freeze-tolerant black mangroves pioneer and the more disturbance resilient red mangroves perseveres. So for how does this mangrove vegetation gradient actually change with the soil? So carbon storage and the sources. I guess Parkin has did a much better job than I do in this part, but we still are doing some research across this gradient with much larger spatial variation here. So we first see is that, let's focus on the left figures, is with the same temperature minimum gradients, we're finding that organic carbon density is increasing with warmer sites along this latitude gradient in general across different depths. But we're trying to project the same organic carbon density data onto the x-axis of mangrove above ground biomass, which is mainly the vegetation part. It has shown a lower explainability with R-squared and also a much larger variation regarding the vegetation here. So it has suggested that more site-specific examinations has to be done with the vegetation impact on the soil carbon here. So that's what we do for the next step. We look at the pairwise or the plotwise differences between each composite soil cores on the top layers and the bottom layers of organic carbon density differences. We found out that the top layer is consistently higher than the bottom layer. So there's an increase in recent years of organic carbon density accumulation. But at the same time, such difference on the right figures is showing no relationship with the mangrove above ground biomass, meaning that the difference that it makes by mangrove expansion itself is not particularly distinct here in Apalachicola than the other sites along this gradient. So to further identify where that increase come from, we also did a isotopic signature study that measured the soil delta certain C that separates some marsh species and the mangroves. And we found out in general, the soil delta certain C decreased with the mangrove above ground biomass, meaning there are of course higher mangrove signature here. But also the difference here is interesting, that is the difference between the top and bottom layer is higher in northern sides of Apalachicola Bay, meaning that suggesting that there's a increase in the soil carbon density by the mangroves itself. So lastly, how will us use this empirical-driven relationship to inform how this mangrove ecosystem properties change continually under the future warming scenarios? So for the vegetation, it's more intuitive, is that we use our relationship generated to project onto the Florida Gulf Coast and also onto different warming scenarios. And the major conclusion we found is, first, for the percent coverage of mangrove and the canopy heights, we'll see that most changes are going to happen here in Apalachicola Bay, the North Florida, and such variation across this whole gradient will narrow into a very small amount, meaning that the Apalachicola Bay here in extreme warming scenarios could have the potential to have the mangroves as tall and as abundant as the southwest mangroves in the southwest Florida. So which is a very critical change to the coastal wetland ecosystem, affecting like fisheries and definitely birds habitats. Well, but as we walk into that future mangroves, so we'll see there are still differences between South and North Florida, with the species compositions actually here is going to increase with red mangroves and white mangroves, but still much of the black mangroves are dominated here in Apalachicola Bay, even in the extreme scenarios. We also found out that above ground biomass will continue to accumulate linearly with the warming scenarios going on. So the last question about how will soil carbon will change, continues changing this climate scenarios, which is I guess much more complicated one, and a lot of other drivers are involved with. But here, just for our study, we have found that the increasing soil carbon storage and the increase in mangrove signature has implied for the mangrove biomass, indicating the growing soil carbon in recent years, especially here in North Florida, Apalachicola Bay. However, there's still a large variation regarding the organic carbon density of those soil cores, and that has resulted in a very low explainability by mangrove above ground biomass itself. So emphasizing there's a lot of site-specific differences that grant further investigations into other drivers, including geomorphology settings, alloxonous input, and nutrient availability. And we're encouraged to open to discussion about how will soil carbon change. So yeah, just to summarize a little bit, takeaway points is that the first, for the mangrove vegetation, we found mostly the mangrove communities and the communities of percent coverage and the canopy height exhibiting a threshold response with the temperature minimum, but above ground biomass still have a linear, rather linear relationship. For the soil carbon density and the mangrove isotopic signatures, we found is increasing with the mangrove above ground biomass along this gradient, but there are substantial site-specific variation here that grants more further study. And finally, in the warming scenarios, we're projecting that the mangrove coverage and canopy height will hardly differ across this Florida gradient, whilst at the same time, the species composition and above ground biomass could still vary. So yeah, thank you guys for listening, and yeah, we have time for questions.
I was curious how well the mangroves respond to those 4 days of 20-degree weather that we had 2 months ago.
Wow, that's a very interesting question, because I just been to Apalachicola Bay, I think 4 days ago, to do that research, and I have photos in my iPhone, and they are all gone. Like this exact photo, I think I took this exact photo on the first page of the presentation, is showing those St. George. Wow, that's a long way. If I can go back a little bit, oh no. Sorry. Could you please don't first slide? Yeah, just the very first. Okay. Thank you so much. No worries. Yeah, just this exact photo, all these red mangroves are no leaf left. I just went there, I think 4 days ago, something like that. So yeah, it's very pronounced effect on the mangroves, but still, like the projection I was talking about is on the long term. On the short term, there are going to be like, randomized or somehow, like opportunity like the freeze event happening. It's going to kill the mangrove for a while, but still a lot of short stratum of mangrove seedlings are preserved to grow up in the future.
So part of climate change, people look at it, figure that you might have an increase in warming, but you also have an increase in variability, which means you're going to have more extremes both ways. So that might counteract some of the mangroves maybe.
Yeah, it's an interesting point, and we have found out like with the temperature data is showing mostly in the recent 4 decades the extreme winter, the extreme low scenarios are happening very small and getting very little in the most recent 4 decades. But for the extreme heat, there might be more, especially in Florida here. So yeah, and for the mangrove, it's mostly the extreme freeze that's affecting the most. Please.
What was your source for your teaming temperature?
The source? Yeah, so yeah, that's grabbed from the graded temperature data from PRISM. It's widely used nationally graded temperature data that has incorporated the weather station, also the model simulation.
Okay, so you're not considering microclimates to show it.
That's another very interesting question that I've been doing for the research. I'm talk more on the microclimates part of it, and I believe Josh has maybe something to share with that as well. But yeah, I think a lot of people are doing that. Thank you.
So yeah, Rachel's got a poster tonight too.
Yeah.
Kind of follow up on the team-in though. So what value do you use for team-in? Is it the average team-in each year, or is it like a historically observed what the minimum temperature was at that location?
Right. That was so that was used for the absolute lowest team-in for the 30-year period. That includes a major events in 1989. From that 30 years along, and the absolute minimum temperature here for each grid. Okay.
All right, our last presenter of this session is Dr. Josh Breithaupt from the FSU Coastal Marine Lab, and he will be presenting vertical change in Apalachicola Bay coastal wetlands. Response to disturbance differs with geomorphic setting.
Thank you, Cindy. I just want to give a shout out and thanks to Annais for organizing this day. It's been awesome. And I will just say that the organization is very clever as well. If you think about this morning, we were up in the river, in the floodplain, and then we went into the bay, and we're doing all the water, and now we're going to finish here with some landward stuff that's kind of all around the bay. So what I want to point out is that I am not Haviland Steinmuller. So the way I'm going to begin this is Haviland is lead author on this project. And the good news and the sad news is that she's gotten a job at Dauphin Island Sea Lab. So she actually has a teaching responsibility on Thursdays, so she can't be here today. But I also want to point out that there are people in this room that have done far more work on this project than I am. There's a good reason I'm at the very end of this list. But Ethan and Sam and Jay and Jenna have all been, and other folks at Annais have been collecting this data set for well over 10 years. So this is really an awesome group effort, and this is kind of a fun thing to talk about. I also want to mention that this paper then did officially get accepted and was published in late last year. So if anybody's interested in that, we can get you a copy. So there's been, I think, a couple talks today that have identified this, but sea level rise is expected to continue, accelerating, right? And what's interesting is if you look at this, this is the tide gauge level for Apalachicola. This is our average across the last, going back to the 70s. So this is our average, 2.82 millimeters a year. But what I want to point out is that in this past decade, it's substantially higher, right? 11.5 millimeters a year. So this is something that's changed quite quickly. And what's kind of neat is this actually coincides pretty darn close with the timing of the data set that I'm going to talk about.
Then just in terms of like what is important is that this is expected to continue. So this is from Sweet et al. Came out last year. This is just basically showing that the rate of rise we've seen since 2000 to the present in the Eastern Gulf is basically, if you follow sort of the central piece of this, is basically going to just repeat itself again for the next 20 years, if not go a little bit higher. So this is important to think about in terms of our wetlands. And here I'm going to give a shout out to work that's been done and been talked about at previous symposiums here. But if you're interested, go to this. This was funded by this Isla program, so the Go Marsh program. And I don't have this animated, but it's the northern Gulf of Mexico, looking at how sea level rise is going to affect wetlands. And so I've just got a screenshot of the Apalachicola one. But a lot of fun to just go play with this in different scenarios if you're interested in this question. So the thing is, these predictions exist, but that doesn't take away from the necessity and the importance of actually doing ongoing monitoring too, right? So one of the things that I'm going to talk about today is the fact that even though we have general modeling predictions of what's going to happen, we have these three very distinct settings. The riverine system in the rivers that, again, we were talking about earlier this morning. We've seen a lot of work out of East Bay and in the backsides of the barrier islands. And so the question is, do each of these respond? Do we just treat them sort of homogenously as the same sort of ecosystem, or do they respond potentially a little bit differently? And there's reasons to expect that they could respond differently. And this is from a great review paper, came out just a couple of years ago, but there's a couple things I want to point out about how wetlands respond to sea level rise. So the first is looking at this little plot here, and this is water depth, right? So there is this relationship that if you have a plant like a Spartina plant and you grow it like in a dryland system, productivity is really low. It doesn't like that. So as water depth increases, you actually see productivity grow up, and then obviously there's going to be at some point where if you get too much water, it's going to drown and it's not good for the plant. But that's really important to think about in terms of the organic material that's produced and delivered to the system, because when you look at a soil under wetland, it's composed of both organic matter and mineral sediment. And the mineral material is a relationship here that's talking about the depth, the frequency, and the suspended sediment concentration of the water that then comes in and floods that system. So that's going to have a very important effect on how much sediment, how much mineral material is deposited to the sediment. So if you think about that map I was showing with the riverine systems versus the barrier island systems or the bayside, these all have sort of different physical factors that are going to control plant productivity or the amount of mineral sediment that's available. So the project is really built around this very simple tool, but what's really remarkable is it's a really, really precise tool. So this is a surface elevation table. If you've never seen it, I'm sure Ethan would be glad to arrange a tour for you to come out and get a hands-on with it. So this is actually called a rod set. So the rod is driven all the way down to the base to refusal or ground level, ground rock. So that's immovable. And then you've got this leveled in center of the system that you can drop a leveled unit with 9 pins that you put at 4 different positions, and you measure the height of those individual pins. It's a very manual process. It's a lovely process when it's buggy and hot. Again, it's very, very precise. And so what actually ends up happening is it's almost like a tide gauge level, because it's telling you the overall width of that sediment, or sorry, of that soil body, how it's expanding or contracting. You pair this up then with this little thing at felspar horizon. This is what it looks like when you first deploy it. And so what you're able to do with that is get a measure of how much material is deposited on top. So I'm going to get to how this is very different. This is measuring the overall thickness of the body. This is just what's being deposited on top. And I'll say this about marker horizons is when they work well, they work well. This is me holding one that's got the, almost like an Oreo cookie. You can see it right in the middle. You can see a very clear, easy measurement there. But I'll just say it doesn't often work that cleanly. So this is what we get in other places. You can actually see sort of blobs of feldspar that sort of got moved around and concentrated in different parts of that work. And then the sediment itself is just a mess when we pull it out, right? So there are ways you can deal with that, but the reason I'm identifying this difference is just to think this is probably the weakest part of our data set in the past, and we've made some changes to it in the last few years to try to get things that look a little bit more like this than like that. And so I'm not going to talk a lot about this. This is just a few examples of different sites. Here's Sam, here's Ethan. This is the first time I went out with them right in the middle of COVID. I think this was like late 2020. So we're all masked up partly for COVID, partly for the bugs. And just to emphasize this, there's over 10 years of data. So we multiple times a year going out and measuring this. This is a long manual effort, lots and lots of data. And this is kind of what the net of that all comes to. And there's a few things I want to point out. Again, for reference, the riverine, the bay, and the barrier island sites. So the riverine sites, what I want to point out just in general, if you look across all these, each of these lines represents an individual set station, right? So a couple things to take away from that. One is there is a difference in the starting elevation, right? You just think about the topography all around the bay. Some are going to be slightly higher, some are going to be slightly lower. But the difference here across this whole data set is about 15 centimeters. At the bayside sites, it's even tighter, about 10 centimeters. But across our barrier islands, and I apologize for the guys on the right side over here, we've got a pretty broad, like there's kilometers between these different sites, right? So there's actually almost a half a meter difference in starting elevations. The other thing to think about is just sort of look at how flat the barrier island trends have been, although some of that's a function of the fact that the scales are different. So I'll leave it there. The other thing is I'll talk about this in a little bit. This is Hurricane Michael and what that did. We look for a signal of that in all of this as well. I'm going to start out with then taking all that noisy data of the individual plots, and you sort of put them together and just think, well, what do we take away from this? So these are accretion rates, and this is what we measure with, again, with the feldspar. So it's just you're using a ruler to measure how thick the sediment is above that creamy filling. And this is kind of amazing, actually. It's like I do a lot of work with accretion in a lot of different wetland systems. This is our average over that whole time period for the riverine sites. That's over, just for changing things, that's 1.2 centimeters a year. That's a really, really high accretion rate. That's pretty remarkable. The barrier islands also, though, about 1 centimeter a year is our average, and then it's lower, down around 5 or half a centimeter, 5 millimeters a year in the bayside sites. Continuing then, just still sticking with the accretion thing, one thing that's fun to point out is just that so if you sort of look down this line right here, the accretion rates across the riverine sites and the barrier island sites, again, they sort of have the same range, but they have very, very different organic matter content. So this goes kind of to what Calvin was talking about. Much, much higher organic matter out, up in the delta, the riverine and the bayside sites, and very, very low organic matter where out on the barrier islands, and this is where the mangroves are located. And this is sort of shown in these cores. So this is a Russian peat core, it's a half barrel core. And in this case, we're actually able to pull up the organic matter. It's actually a beautiful, beautiful core. This is all sandy out on the barrier islands. This type of coring device doesn't work in sand at all. It's stuck right away. So very different between those two. But what I want to just, a couple things to point out is that there's a strong relationship in the riverine sites that as you increase organic matter, you increase your accretion rate. So basically the organic matter is driving increased accretion at these sites. It's not all mineral sediment, but it's the opposite in the bayside sites. And this is kind of cool because I think basically what this is representing is you get higher accretion. If you look at basically where the channels are at, you get greater accretion where that sediment material can get there. And then it tapers off as you almost sort of get into lower depression elevation, interior areas, sets that are a little bit further away from where the water can deliver the sediment. So going from accretion then to elevation, this is a very different story than the accretion, which you remember was all over the place. There's no significant difference between the average rate of elevation change between all these three different systems. And for context, there's the accretion rates, right? So here's the really key thing, and this is cool because this is something I've actually preached in a lot of my other work that hasn't been using these tools, is that accretion is not a good predictor of elevation change. So what you're ending up happening is you're depositing lots of material at the top of this sediment, but the net effect is it actually somehow different processes shrinks and gets lower, so that the net elevation change is not different between all these systems. And I mentioned this earlier, but just the idea of what Hurricane Michael might have done. So this Haviland ran some breakpoint analyses on all the combined setting, all the combined data sets for each of those geomorphic settings. And the thing to take away from this is that the barrier islands don't actually show a significant difference between the data before and the data after Michael. But the other ones, both the bayside and the riverine especially, show a significant uptick in rates following Michael. And this is kind of puzzling to me because what I've seen in other places is you'll see the hurricane happen, you'll see a large deposition of sediment, maybe a burst of productivity that follows after it. And so you'll see kind of a short-term bump up, but then it kind of returns back to equilibrium. And these both have actually continued that trend upwards. So the question is this going to come back down, or is there something else that's going on? And that's going to take more work to figure that out. This is a lot of data. There's a lot of information here. But what I want to point out, this goes back to that initial slide that I was showing the different sea level rise rates. So this here is the long-term rate of sea level rise. This is that more accelerated higher rate that we saw in the last decade. And the thing to take away from this is that the high organic matter sites, this is indicated by the dark blue bars. These are the riverine sites, and there's more indication that they are capable of dealing with these higher rates of sea level rise. At least they're going to be more on par with the rate of sea level rise than the other sites. And then I'm going to conclude with this slide, because this is kind of the conundrum with this, is that everything we're measuring with the sets is based on vertical change. And if all you do is measure vertical change, you miss that there's actually maybe something happening over there laterally coming in your direction. So these are all three of the barrier island sites, Pilot's Cove, Nick's Hole, and Unit 4. And this is aerial imagery back from 2013, 2019, and then the present day are on the ground photos. And so these were not intended to be subaqueous, subtidal sets, but here we are about 10, 12 years later. The outermost sites are now permanently inundated by water to the extent that this one at Pilot's Cove has actually now got seagrass under it. And then this one on Unit 4, so this is the one, if you take the bridge out to St. George and just hang a left, you can actually walk into the site, which is one of my favorite sites to take people. We've watched this sand berm move in. Basically, I got here in 2020, and I've kind of watched the sand berm just move and move and move and move every time I go out there and visit. So I don't know, Ethan, what it looks like now, if it's still there or if the center post is gone, but there's no trend. You don't see it in the trend, right? Like until you get the sand berm moving in, but these ones, you don't see this lateral erosion that happens until it's too late. So all this to say that there is actually a sea level rise effect occurring on the barrier islands already. And so with that, I'll say thanks for the time, and thanks again to Annais, and if there's time, which I think there is, I'll be happy to take any questions.
Just a question about like the huge difference between TOC in the barrier island and also the riverine. So I'm wondering, like, the marsh, the vegetation, they're probably similar, I guess, like similar species, similar coverage. Why do you think that, like, on the top layers, maybe even there are still huge differences between the barrier island and the riverine and the bay?
I think primarily it's a marine sediment, so there's just, it's much sandier, much sandier out on the barrier island. So there's just a greater supply of that mineral sediment than you get up in East Bay, which is kind of it's more distant. So you'd have to have very, very frequent high flooding events for that to get a lot of mineral sediment. And the same in like the sites on the rivers are really remarkably high organic material. There's just not as a lot of sediment coming down them versus like the main stem of the Appalach would have a lot more, like Kevin was talking about, examples that if you go and drop cores off of like the main stem of the Appalach, that's really sandy. But as you get out more into those side rivers where the set stations are located, it's not as sandy, it's much more muddy, much more organic. So it's kind of like we were talking about earlier, it's kind of like more of a local geomorphic geologic control.
Yeah, like even with the salt marsh trying to create in the barrier island, there's still a huge difference.
There's a huge difference, yeah. Jenna, sorry, I think you had a question. No.
Maybe I have a silly question. If you had a time machine and you go back 15 years, where would you have put the sets instead?
Well, this is the thing it's fun when you look at all the set literature. They always talk about how sets are installed for very particular questions, particular investigation, and then invariably those questions will change. And that's, I think, what we're dealing with. It's honestly global now, is the set stations were initially installed like the late 90s, early 2000s, last decade or so. And now all those projects, which generally coincided with someone's PhD project, so you can get 3 years of data before you can turn around and publish it. All those are generally getting older and longer, so they're changing hands and the objectives are changing. So I don't know if it's a fair question to say what you would change, because my questions now are, different than your questions would have been then, maybe. But all I can say is maybe the mangroves would be the one thing that we don't really. Unit 4 starting to see mangroves, but if we could get one in the Pilot's Cove or something that's more located where the mangrove expansion is occurring. That'd be interesting.
I can say we chose originally mainly because of vegetation types.
And I think like just looking at Haviland's analysis, it was well done because you get these 3 differences.
But now we've got seagrass and I originally had sparse before, so.
But maybe that's an actual reflection of environmental change in the system.
Just curious real quick, because I still try to wrap my head around why the difference after micro, that you don't see it going back to that normal rate.
Yeah, no.
It's just weird.
It is really weird. So it could be a productivity thing. I didn't show data today because, we did in-growth bags to look at root growth, and the numbers are just off the charts. They're higher than any, like for the sawgrass and the cypress, they're higher than like 2 to 3 times higher than any sawgrass below ground productivity numbers I found in the Everglades. So there may be a productivity thing going on, but I didn't show the data partly because I'm skeptical. There's got to be some kind of miscalculation going on. But yeah, I don't know.
Any other questions? Okay, well, thank you so much. Thank you all for joining us today. And